And unfortunately, what I have to share, I've got 6 students here. Let's see if that's right. 1, 2, 3, 4, 5, 6. That's right. Let me make sure nobody's in the waiting room. They're not. Okay. So if y'all don't have anything to share with me, I've got a little bit, well, it's quite a bit, I guess, to share with you. We'll go from current slide. That's where we'll be heading. Okay, there we go. I think I told y'all a lot on last Thursday, though I didn't know everything I know now, so let me fill you on some, fill in the blanks a little bit. There are 2 things happening this week and next week that could easily impact this class. Hopefully not negatively, but it could impact it. Okay, here's the first of them, and this has the greatest potential for impact. I think I told y'all last week that I had blood work done on Friday a week ago. We saw the results. My white counts were really through the roof. So I knew anyway before that I'd need a treatment. This is coming up sometime soon, but they were much higher than I was expecting. And then when I saw the doctor last Tuesday on a telemedicine thing, he was he was very concerned and wanted to do more blood work to make sure the anemia that I was having, which is why I run out of energy so fast. Jacob is just coming in, so let me get him here. Okay. That wasn't being caused either by the disease or by the treatment. And also he wanted to check and make sure the markers for the disease were still the same markers so that the treatment I'm getting is the right treatment for me. Both of those checked out positively. No sign of any problem with the anemia except it's there. And no, all the markers are still like they were, indicating that still on a good drug. However, the counts are so high, and evidently they've had some problems with this drug, not necessarily UAB, but across the board. Problems with this drug. It's a monoclonal antibody that it is so effective, and it has always been with me. I mean, when I get a treatment, the counts just plummet. They go down like crazy. Well, my counts are so high now, they're worried with the counts being this high that to take a full treatment in one day might drive too much into my system too fast, too many destroyed cells, and cause yet another problem. So they're doing 2 things. Number 1, I'm starting this evening taking a sort of a diuretic type thing so that it flushes stuff out of my system more easily. Okay, so that's the first thing. Now here's Brianna. I thought she was already here. She was, so that's not a new student. So we should still be at 7 students. Let's see if that's right. 1, 2, 3, 4, 5, 6, 7. Yeah. Whole cluster down in the middle of the alphabet. The top, Angelita's holding it down all by herself, and the bottom, nobody's there. So hopefully some will be coming in. So anyway, so I will be starting the diuretic this evening. That's no problem. But here's where the problem comes in. They wanted to do 2 days of treatment rather than 1. 10% the first day, 90% the second day, if there's no problems with the first day. So evidently this drug, and it is really effective, they are wanting to take it slowly on it. So what that means is Thursday morning at 7 o'clock, I'll be at the infusion clinic, and hopefully they'll get started on me fairly soon after that. And they said it might take 8 hours. Hopefully it won't. But what that means is my 8:30 class, out of there. My 10 o'clock class, out of there. My 11:30 class, out of there. However, this class, I hope that I'll be back by 3 o'clock. If I am, hopefully we'll get started at 3:15. If I'm not here at 3 o'clock, 3:15, and you're waiting for me, don't give up. I mean, you might go on and do other things or whatever, but check periodically to see if I've opened the class or not. I'm hoping everything goes very smoothly, and here comes Valerie, and if it does, I'm hoping to be back here before 3. But I can't guarantee that now. Now here's the other issue. Another issue. They give me Benadryl before the treatment. They give me 2 Tylenol, which I don't take much medicine, so 1 Tylenol is all I ever take for myself if I have headache, muscle ache, something like that. 1 is all I ever take that does the job. They give me 2 across the board. Okay. And they give me some steroids and other things like this, trying to minimize reaction. And they give me a Benadryl. And Benadryl knocks me out. So within 30-45 minutes of the Benadryl, most of the time I'm out. Okay. Now, hopefully I will sleep it off before I leave to come back home. So hopefully when I come back home, I'll feel well enough to go on and have the class. So if I start nodding off in class, somebody yell, wake me up or whatever, and we'll keep going. Or I'll say, look, I'm just too tired, we can't do it. But I just wanted to let you know, on Thursday, there is a minor chance, my dog just came up to see me, a minor chance that I won't be here right at 3:15. I'm hoping I will be. There is a more minor chance that even if I'm here, I won't feel like teaching. That hasn't happened before, but we'll have to see. And 4.5 hours is a bit long, so I don't know if I'll make the whole deal or not. And then one other little issue. I do not have the next lab ready. I have the lab ready for today. I just put it out there within the last half hour. Okay. But the one for Thursday I don't have yet, and I don't know if I'm going to have time to develop it. I'm going to try to, but we'll have to see. We'll see how far we get today, where we're likely to be. So we may not be ready for the lab. I may not feel like doing the lab anyway. We'll have to see how that goes by Thursday. Okay, if I can get it done, I will. Okay, that's one side. That's the major. Okay, now with that, the other part of that is my office hours on Thursday are basically going to be eaten up by the treatment and getting back here and that kind of stuff. So I won't be available from 1 to 3 on Thursday like I put down as my office hours. Friday I will have the full the 90% treatment, and that will be going from 8:15. Why they started later, I don't know. They probably just were too full on Friday. From 8:15 probably until 4 or 5 o'clock in the afternoon. So I will not be available for any office hours on Friday. I probably will not be available for any emails, because in the Kirkland Clinic it's really hard to get a signal. Okay, and they have a public access thing, but lots of people get on it. If I don't get on it early and fast, I may not be able to get on it. So I may not be able to answer emails, and then I may be sleeping. So because that's going to be the tougher treatment, not tougher, but there's a more likely chance it'll last longer and I might be sleeping. Okay, so Friday, just consider me to be out of pocket. If I'm able to get on email, I may be responding to emails, so you may hear from me, but that would be about all. Okay, so that's that side of things. Here's the other thing, and this one I think I mentioned last week. A really good friend of ours died on Thursday of last week. It was just before our class, the class before mine. I got word on it. I'm the contact person for her. She has no family here in Birmingham. She has no family in the state of Alabama. The closest anyone knows possibly is a sister in Virginia, but they were not close. They haven't communicated in years. The sister was many years older than her, and she was 76, so the sister would be in her upper 80s, maybe into their 90s or close to it. So I'm the contact person. So I've been being contacted by members of our church, by the pastors, by the chaplains, by the UAB, because she donated her body to science, and UAB has her body. I've been the contact person for her belongings, for her bank accounts, I mean, I'm having to handle a whole bunch of junk with that. And for instance, the 2 hours I had between class, my office hours a day from 1 to 3, more than half of that time was spent on the phone, either with the social worker, someone from our church, trying to get in touch with the chaplain. There was just one thing after another with that. I did get time to finish your lab today, just barely. I mean, I didn't have more than 10 minutes to spare, or 15 minutes to spare on finishing that. You'll see that the time that, if you see the time on it, it was pretty recent. But it is ready to go, and somebody has just come into the waiting room. It's Tobias and Rucker. So let me get them here. There's Rucker. And where in the world is Tobias? There he is. Okay. Good deal. We got a little bit bigger class today than we had a few minutes ago. All right, Tobias and Rucker, I don't know if you can hear me yet, but I was just saying this is a weird, strange week for me. It may have some impact on this class. The major impact being that I am scheduled for an infusion for my leukemia on Thursday that I wasn't expecting last week. So, but it starts at 7 in the morning. Hopefully it'll be done before 3 in the afternoon. So if it is before 3, hopefully I can be home by 3:15. But there's no guarantee of that. Now I'm going to send out the Zoom invite for 3:15. But if you can't get me, if it doesn't indicate that I'm there waiting, just check every few minutes. Every 3, 4, 5 minutes, something like that. 5-10 minutes or whatever. Hopefully I'll be home sometime in that time frame and we can have class. Now what kind of shape I'll be in, I don't know. They give me Benadryl, that sort of knocks me out. Hopefully I will have slept off the Benadryl before I get home for class. If not, we may have to curtail part of the class and end it early. I don't know. Hopefully not. Okay. The second issue that's happening this week, and I was just telling them this, is a lot of my office hours are being eaten up by having to deal with my friend's death, because I'm the contact person, and there's just all sorts of things I'm having to deal with. I can't deal with them after hours because no one's in the office after hours, so I have to deal with them now. So for instance, tomorrow morning 8 to 10 I have office hours. I know I have to do a little bit with that, hopefully not too much. Okay, 4 to 6 tomorrow evening, I may have to be at Episcopal Place for part or all of that time. Right now I'm scheduled to do it. They've taken care of some of that for me, so I may not be there the whole time. So my office hours are being affected. But then on Thursday, like I was saying, I'll have 0 office hours to speak of, mostly because I'll be in treatment pretty much from 7 till around 3 or so. If I get home before 3, I'll have some office hours, but there's no guarantee of that. Friday, 0 office hours at all, because I'll be in treatment from 8:15 until probably 4 or 5 o'clock in the evening, okay, late afternoon. So anyway, that's how this week is shaping up. Sorry about that, but we will pick up and go with where we left off last time, which is right about here. If you've got your books, this is on page 27 in your book. If you have the big book, if you have one of the little books, it's on 2-3, chapter 2, the 3rd page in chapter 2. All right. We had just started talking about measuring motion. So before I get going now, are there any questions? Can I clear up anything? Or did some questions come up while I was talking, or when y'all came in you had a question but I was running my mouth so much you couldn't get it in sideways? Anyone have a question? Oh, she just went back downstairs. I wish you could have seen her. She's a cute, sweet dog. She's a golden retriever, but she's one of those they call the English creams. She's a white golden retriever. She's just as pretty as she can be, and she's just as spoiled rotten, and she rules the roost too much here. So she came up to see me when I started talking, and then decided I wasn't any fun, so she went back downstairs. Okay, so sorry, I wish I could show it to you. I was thinking of tilting the camera so you could see her, but that would take both hands, and I was rubbing her with one hand, so I couldn't do it. Okay. All right. Any other questions, issues, or concerns? Very good question, by the way, though. Okay. All right. Well, where we left off last time, we were talking about measuring motion, and the first way we measure, well, we talked about you measure position, you measure time, then you put the two of them together. The change of position with respect to time, that's called speed. You can think of this as change of distance with respect to time, and that's what they say here. Speed is equal to distance over time. When they're talking about position, they have to almost say change of position, because you start at a position. The position has nothing to do with your speed. It's the change of position. If you went there, that would be different from here. Okay, so change of position with respect to time. And sometimes they even put it in there with respect to the change of time, because it's not the time of day that matters, it's the time that the event happened, the time over which you were changing position. So quite often the formula is written like this. Okay, if I can find my pen, where in the world, there it is. Okay, that speed is equal to change of position or distance, I'll put D for distance, over change of time. Now, one reason I did this, rather than writing out change of, I put delta. That's the Greek symbol, capital Greek symbol for the letter D, delta. And the last hurricane, remember, was delta. Okay, same type word. Okay, it's a triangle. It's supposed to be. Mine doesn't look like it. That means difference in distance, difference in time. D is for difference. Okay, so it's the difference in, so it's the change of distance over the change of time. Sometimes that's a far better formula to use than just distance over time, especially if you're thinking position. What the position is has really nothing to do with it. It's the change of position. Now, this is also talking about, most of the time, average speed. Okay, the average speed is your most common measurement. Okay, and you know how far you traveled, you know how long it took. That's your average speed. However, quite often we're really more interested in instantaneous speed. So let's say I got in my car to drive to the Bessemer campus. Okay, now I'm just going to round off the numbers here. It's about 20 miles from our house to the Bessemer campus, say. Okay, now let's just say it took me 30 minutes to get there. That's moving along pretty well. So 20 miles in 30 minutes would be about, the average speed would be 40 miles per hour, because half an hour, I'm using just round numbers. Sometimes it takes longer than 30 minutes, okay? But just to keep it rounded, that would be 40 miles an hour. Does that mean I was driving 40 miles per hour to get there? No, okay? Backing out of my driveway, I'm not going to go 40 miles an hour. Going to the first turn, I'm not going 40 miles an hour. At the stop sign, I'm not going to be going 40 miles an hour. Okay, and I got a lot of stop signs between here and getting out of Southside. Okay, now once I get on the interstate, I'm going to be going faster than 40 miles per hour. Otherwise, I'm going to be hitting the back. So you see there's a difference between your average speed, which is the distance traveled divided by the time. 20 miles in 30 minutes. Okay, that's the average speed of 40 miles per hour. What we're often more interested in is the instantaneous speed. That's the speed as your delta t, your time interval, is going to 0. So you see this time interval, that's what delta t means. Not time as in time of day, the time of travel, we're talking about an infinitesimally small amount of time. That's your instantaneous speed. If you were to use your odometer and your watch or a clock in your vehicle to do average speed, that's exactly what you get, distance over time. To do instantaneous speed, that's what the speedometer does. And it does a pretty good job of telling you how fast you're going at that particular time. Okay? Won't do any good to talk to one of those flashing blue light guys and say, oh, but my average speed wasn't breaking the speed limit. No, that won't work. They're measuring instantaneous speed. So the time interval, the delta t, the denominator, is approaching 0. That gets into calculus. We're not going to get into that now. Okay? Now let's see. Here is the, I thought they were going to show it here. Maybe they will. Let me go. Nope. Okay. Let me, also on page 27, here is the formula. Let me go back here. I put that. Here's what they do for average speed quite often. If I can get my pen to show back. There it is. V bar. Now usually V stands for velocity. That bar is not a vector symbol. That would have an arrow on it. This means average speed. So that's what this is talking about right here. Average speed, V bar, is equal to, and they use the symbol D also, over T. Okay. Understanding this is change of displacement over change of time, or distance you traveled over the time it took you to travel. That's your formula, equation 2.1 on page 27. Okay, now let's use that in the next slide. So here's an example of average speed. Here's a car. He's been going along, and his, say, odometer or whatever he's reading said 50 kilometers here, 100 kilometers there, 150 kilometers there. This took him, he was at past the 50 kilometer marker on the interstate, say, when it was 2 o'clock. I don't see. Yeah, okay. No, 1 o'clock. Okay, at 1 o'clock. At 2 o'clock, he passed the one saying 100 kilometers, and at 3 o'clock, he passed the one saying 150 kilometers. He must have it on cruise control, okay? So, what is his average speed over this time period? Well, the average the distance traveled is, now, okay, let's go back to those deltas again, okay? In fact, I think I'll go back to that slide. Okay, what does that delta really mean? Remember, it means a difference. Difference means subtraction. So it's D final minus D initial. Always final minus initial. When we do the lab today, we're going to be using that over and over and over again. And the delta T is also T final minus T initial. That's what delta means, final minus initial. Whatever follows the delta is the final one of those minus initial. You always measure it that way. So therefore, here we go. Calculate the average speed between trip times of 1 hour and 3 hours. So he has his trip timer on, he has his odometer on, and he finds out it was at 50 kilometers when he started this at 1 o'clock, and at 3 o'clock it was 150 kilometers. What is his average speed? Well, that's the V bar is equal to change of displacement over change of time. Okay. Change of displacement would be final minus initial. So that's 150 kilometers minus 50 kilometers. And they give you the times right here and the change of time was from 3 hours minus, always final minus initial, 1 hour. Okay. Now, what does that give you? 100 kilometers. The difference between 150 and 50 is 100, and the difference between 3 and 1 is 2 hours. So what was his average speed? 50 kilometers per hour. Notice the units are your friends. Treat them just like you do the numbers. Divide the numbers. 100 divided by 2 is 50. Leave your kilometers over hours, kilometers per hour. Does that make sense? Okay, y'all probably do this all the time when you're driving or calculating how far to go, when you'll get there, when you need to eat, whatever. If you're ever traveling. We don't travel much anymore, but when we do, yeah, we do that. All right, no questions? Let's see how they answered it. Okay, there was a formula. I'll go on and erase my scratch so it won't be bothersome on here. So there was your formula. V bar is equal to distance over time. What was the distance? What was the time? They didn't use the deltas, so you have to do the subtraction in your head. Well, they just did away with it. Wow! Oh, wait, I hit the wrong key. Go back where we were. That's interesting. Okay. No. They don't show the answer, but we've shown the answer. It's 100 divided by 2, and that's 50 kilometers per hour. Now that's not that fast, folks. That must have been city driving, but boy, city driving, that sure was very, and what we call this, because it was 50 kilometers that hour, it was 50 kilometers this hour, he was going at very close to what we call a constant speed, uniform speed, not changing. Now, of course, we don't know that. All we know is that he was at the 50 kilometer marker at 1 o'clock, at the 100 kilometer marker at 2 o'clock, and at the 150 kilometer marker at 3 o'clock. But guess what? He could have stopped in here. He could have, gotten gas. He could have done anything, but driven a lot faster in between. He just happened to be, his average speed was 50 kilometers per hour the first hour and the second hour, and of course over the 2 hours it was still 50 miles per hour, kilometers per hour. Okay. Now that was speed. What's the difference in that and velocity? Well, let's see, we're not quite at velocity yet. If you turn the page to page 28 or 2-4 in your smaller books, we have another problem showing up here. So let me see if I can put it on this page. If not, I can go to a white page. Yeah, let's go to a white page. Let's see. All right. Yeah, this is a pretty good problem. So let's go to the white page. Whiteboard, they call it. All right, I got a little more housekeeping to do. Y'all can't see this, but I have a toolbar, taskbar that they put in the white space, so I can write there. And they also have the white space underneath some of your names, which you can't see. So I'm going to move the whiteboard over to the left as far out of your space as possible. Okay, and I'm going to move it up as close to that toolbar as I can. Okay, so now it gives me the most space. Here's example 2.1. I think I'll put the book in my lap so it's a little easier to read. Okay. The driver of a car moving at 72 kilometers per hour. Boy, they're liking their metric system, aren't they? 72 kilometers, that's supposed to be an M there, per hour. What is that a measure of? What do we measure in distance over time? Speed, excellent. Okay, so I'm going to call that V bar just for now because they've been calling it V bar. Speed, which I could use S or V bar. So that's the speed. Oh, and I forgot something, didn't I? That was 72.0. That means to the nearest tenth of a kilometer per hour. That's how fast you're going. Now this driver drops his road map on the floor. Guess what? In the old days, people used road maps. Y'all probably don't even know what one. No, I'm just kidding. It takes him about 3 seconds, so that's the time. And I would say a delta t, a time interval, would be 3.00 seconds. Boy, to the nearest hundredth of a second, that's pretty precise, okay? To locate and pick up the map. How far did he travel in that time? So, oh, here comes Diana. She was already here, so she must have had to bounce out and bounce back in. Make sure I've got her marked here. Okay, I just heard a boom bump. I don't know what that's about. Wasn't my phone, so whatever. All right, now if you remember from the first chapter, I told you that there are ways to do problems. Remember the one that we had was the formula was V bar is equal to, using the books thing, distance over time. Okay? Now this one says, how far did he travel? How far? What answers that question? The distance. That's the unknown here because that's the question. Now here we have V bar, we have our T, and we have the D also, but it's not in the right order. We want to solve for D because that's what we're looking for. So here's what we can do. We can multiply both sides of this equation that we know by T, and it doesn't matter really where you put it. That gets rid of the T here, and that gives us D is equal to V bar times T. And you know that, don't you? Because how far you travel is how fast you're traveling times how long it took. That's your distance traveled. Okay, so now with that form, we can plug in the V bar, 72.0 kilometers per hour. This is per hour. We're in seconds here. We need to do some changes first. So let's hang off on this for a moment. Let's hold on this. Okay? We need to get that to something a bit more reasonable. We're talking about seconds, not hours. So let's take our velocity there, V bar, and that's 72.0 kilometers per hour. Now, what these are conversion factors. Now, what units do you think you probably want to wind up in? Okay, we know we want to round up with seconds, so seconds is going to be down here in our denominator. What you think would be reasonable in the numerator? You think kilometers per second? No, you're not going anywhere close to a kilometer. So what would be a good numerator to have? A second is considerably shorter than an hour, so you want a smaller unit than a kilometer. What would that be? Maybe meters. Meters per second. Now, what are all these blanks here? Notice they're in pairs. These are multiplication, meaning you're going to multiply your conversion factors. There's always a pair. The first blank is for numbers, the second blank for units. Numbers, units, numbers, units. My suggestion and rule that I follow, always put the units in their place first. Then match the numbers with the units. Okay? Now which one you want to tackle? We got two conversions to make. One is kilometers to meters. I can't get my pen to agree. Kilometers to meters. The second one is hours to seconds. Which one you want to go for first? It really doesn't matter. Someone say. Hours to seconds? Is that what you were saying? Or did you say hours to minutes? That's a pretty good thing to say. So let's do hours to minute. Now remember the blanks are for your units. So since the hours is in the denominator here, I want hours in the numerator here, so they will cancel out. And that will leave me minutes. Now don't just leave it M, you would think that's meters. Minutes in the denominator. Now that you've got those in place, match up the numbers with the units. How many hours in a minute or how many minutes in an hour? You tell me. Anybody? Surely you know. You do know. 60 minutes is 1 hour. They're exactly the same. That's what makes it a conversion factor. So now we would have kilometers per minute on this side, but meters per second on this side. So we need to make another conversion. We need to either go kilometers to meters or minutes to second. Which one you want to tackle? Minutes to second. Which of those two that you just named, minutes and seconds, one goes on top, one's on bottom, which goes where? Always put... Okay, look at that. What happens if you put seconds up here and minutes down here? That would leave you kilometer seconds per minute minutes, minute squared. I don't want that. So I'm going to have to find my eraser again. Okay. So how much you think it would go? Okay, good deal. Minutes on top and seconds on the bottom, and guess what? The minutes will cancel out and it leaves you seconds just where you want it, on the bottom. Okay, now the question to ask yourself, how many minutes are in a second or how many seconds in a minute? 60 seconds is exactly 1 minute. There's your conversion. Okay, the last one we have is kilometers to meters. So one of those units is going to go on top and one's on the bottom, which goes where? Meters at top, you're absolutely right. That's just where we want it. Putting kilometers in the bottom, that's exactly where we want it, so the kilometers will cancel out. And then the question you ask yourself is how many meters are in a kilometer or how many kilometers in a meter? Which way does that go? What does the metric prefix kilo mean? Say again? 1,000. There's 1,000 meters in 1 kilometer. 1,000 grams in 1 kilogram, 1,000 liters in 1 kiloliter. I mean, anything that you would choose to do, kilo means 1,000. So on the street, that means 1,000 grams. Oh, we don't talk about that. Okay. Now we've got our conversions to do. Now, here's something just by the way. There are exactly 60 minutes in an hour. There are exactly 60 seconds in a minute. There are exactly 1,000 meters in 1 kilogram. So we don't worry about significant digits here. You could put 0.000, you could put 0.0000, you could put a 0.000, you could put as many zeros as you wanted to, because these are exact conversions. Now, if you had something like feet and meters, that's not an exact conversion. You'd have to go with however many decimal points they give you. But this one, you got it as many as you want, so don't worry about significant digits there. So what do? We multiply numerators, divide by denominators. Now I'm really lazy, so I'm going to do this, but you don't have to do this. I'm going to divide out a 10 right now. That would wipe out a 0 in the denominator and wipe out a 0 in the numerator. I'm going to do another one just because I don't like punching in more digits than I need to. So I've wiped out 2 of the zeros here. Now I could, if you wanted me to, go 6 into 72, and that would go 12 times. And since I'm really lazy, I'm going to do that too. 6 will go into 72 12 times. But this 6 will go into 12 2 times. So just in my head, I can have this defined. This would be 2 times 10. That would be 20 meters per second. Because I wiped out all our denominators except ones, and that's 20 meters per second. I didn't even need to pick up my calculator. Sometimes you will. Don't feel like a Lone Ranger if you don't, but this is exactly 20 meters per second. That's now my velocity, distance over time. So now I can put this up here and do 20, ooh, that's ugly, meters per second. That's your velocity. And their time, which, well, I had a t there, but it crossed it out. The time here was 3 seconds. That will work, okay? Now, I did mess something up there because we had 3 significant digits there. This really should be 20.0 seconds. Multiply by 3, and that would give you 3 significant digits there too. That would give you 60.0, 3 significant digits. This second here, cancel that second there, and that would give you meters. 60 meters. Wait a minute here. What is 60 meters approximately? Any of you have a clue? A meter is a little bit longer than a yard. So this is 65 or so yards, maybe even further than that, okay? Somewhere in that neighborhood. Okay, guess what? That 3 seconds it took them to pick that up off the floor and sit back up traveled more than half of a football field. In fact, awfully close to 2/3 of a football field. That's quite a ways. Anyone could have jumped out in front of him. Any kid could have kicked the ball out in front. A deer could have run across. Anything could have happened in those 60 meters. That's how far he traveled in those mere 3 seconds that he bent down, stooped down, and tried to find that map and pick it up again. That's why it's a good idea not to be dropping things and trying to pick them up while you're driving, especially at that speed. 72 kilometers per hour, that's moving along pretty well. We could have, if we had wanted to, figure out how many miles per hour that was. That would have been a little bit easier conversion here in a sense. This was pretty easy because everything went in easily, but you could figure that out as well. Same way. All right, and that's what they got in the book, 60.0 meters. Okay, any questions on that? All right, if there are no questions, does anyone need me to leave this problem up a little bit longer? I hear no objections, so I'm going to clear the drawing. Okay, now let's do example 2.2. A bicycle has an average speed of 8 kilometers per hour. So there again, V bar is equal to, and boy is this ever precise, 8.00 meters per second. Okay? No, it isn't kilometers per hour. I wasn't paying attention. Okay, it's kilometers per hour. Okay, that sounds about right. How far will it travel in 10 seconds? So the time, or the delta t, time interval, is going to be your 10.0 seconds. Okay, now, again, we have a problem with our units, don't we? So let's take this right where it is and do our conversion factors. And because this is a very similar problem, different numbers, different scale, but a very similar problem to what we had before, we're wanting to find that speed in terms of what we did before, how many meters per second. We didn't have to do meters, but that just is what makes sense, and that's what they give their answers into. So do you remember how we did this? Someone explain to me what my first conversion is going to be. Doesn't matter which one you do first, pick one. Anybody? Ultimately, we need kilometers to meters. We're going to need hours to seconds. In case you don't know that directly, you might do hours and minutes to seconds. So which one you want to do first? Anybody? Hours to second. You want to do it in one step or two steps? Texas two-step or one step? One step? Do you know how many? So if you do it in one step, you'd put hours up here and seconds here. Do you know how many seconds are in an hour? That's what I was asking. No. Okay. Okay, you're looking it up? Okay. You can do that if you want to, or you can. You're absolutely right. 3,600. Yuck. 3,600 seconds in 1 hour. Okay, so this means since I cut off that, I won't need this conversion over here. Okay, so that got your hours to seconds. That's exactly what you wanted. Now we got to do kilometers to meters. So which one goes where? All right, you're trying to get from kilometers to meters. That means kilometers, one goes on top, one goes on bottom. Which goes where? Kilometers and meters. Which where? If you put kilometers at the top and you multiply, that's what these dots mean. That gives you kilometers squared per meter. Ooh, we don't have any kilometers squared over here. You don't have a per meter down there either. So units are your friend. Yeah, the other way around. Units are your friends. Be nice to them. They will help get you out of trouble. Come on. This thing drives me nuts. Okay. I think I erased too much, but I can go back and do it. You want meters on top and kilometers on the bottom. Okay? This pen is acting really strangely. Okay, so that will wipe out your kilometers here and leave meters per second. Very good. How many meters in a kilometer or kilometers in a meter? Anybody? 1,000. You got it. 1,000 meters is exactly 1 kilometer. Okay? So we take the 8, divide it. Now I'm going to be lazy again. I'm going to wipe out these 2 zeros and 2 of the zeros here. So I could do some more, but I know I'm going to run out of possibilities in a minute. So let me just do it. 8 times 10 is 80 divided by 36. That one I will get my calculator out and do, which is my phone, which is now charged. So let me find my, there it is. What did I say? 80 divided by 36 equal 2.22 meters per second. So we round that. The 2's kept on going forever, but what you do, since you have 3 significant digits here oh, you actually had more than 3 here, more than 3 there. You have 3 here. Everything they gave you was 3, so let's use 3 digits. You have 2.22. So count 3 digits. There's 1 digit, 2 digit, 3 digit. Look to the right. It's 2. That's less than 5. Throw the rest of them away. If that 4th digit had been a 5 or more, you'd bump that 3rd 2 up to a 3. But it wasn't, so that's, I don't know why it makes random marks on the thing, 2.22 meters per second. Okay, I'm sorry. Yeah, 2.22 meters per second. That's his velocity. Now we go back to answer our real question. Our real question here was, how far does it go? Yeah, so again, our question was, how far? I don't usually write them in, but that is asking for a distance. That's your unknown. How far? The distance. Okay, so what is distance? Like we did before, distance is equal to average speed times time. And our average speed here was 2.22 meters per second. Multiply that by, excuse me just a minute, it was a little stuffy in here, now it's getting a little cooler, so I'm going to try to, if I don't trash something here, turn off my ceiling fan. Okay, sorry about that. Y'all don't want to hear me sneeze, I promise you that. It's pretty awful. Makes the dog jump and my wife scream. It's just terrible. Okay. Alright. So 2.22 meters per second multiplied by the time. The time was 10 seconds. 10.0 seconds. And that would simply be 22.2 meters. Let's see if that's what they got. That's exactly what they got. So that bicycle traveling at 8 kilometers per hour would go about 25 yards, okay, in 10 seconds. And that seems pretty reasonable. Okay. That was example 2. 2.2. All right. Put that aside. Excuse me just a minute. Since I'm really anemic every now and then, I need a little more energy boost. And I forgot to bring up a Coke, so it's just going to have to be water now. Now I'm feeling hot. This is rather strange. Okay. There is a concept supplied at the bottom of page 28. Speed style or style speeds. Yeah, it looks like sort of a dorky kind of question, but if you're into it, look at it, think about it. Top of the next page, how fast is a stream? Well, one way you could do that, stream, you think you're out in the woods somewhere. If you got a measuring tape, or you can trust your strides to give you approximately a distance, you can measure, walk, or measure a distance, especially have someone helping you, a certain distance up the stream, and your partner stays back on the, say, a bridge or something, a log, or right there at the edge of the stream, and you measure the distance, and then when on a given signal, someone starts a stopwatch right as you drop a leaf into the stream, and then measure how long it takes for that leaf to get down here. Distance divided by time is speed. That would be how fast is the stream. Okay. Isn't that enough of that? Again, kind of bizarre, but okay. Oh, here comes Dreshon. Dre. I think he said he goes by Dre. Let me see if that's right. Yeah. I believe so anyway. So Dre or Dree is here. Dre, I think it is. Now, for any others that may have come in recently, let me go back and say this. I am now scheduled to have an infusion for my leukemia on Thursday. I didn't think they were going to do that, but they are. They're going to start at 7 in the morning, and they said they figure it will be about 8 hours. I'm hoping they're being extravagant with that estimate and that I'll be out of there before 8 hours is over. But nevertheless, my 8:30 class trashed, my 10 o'clock class trashed, my 11:30 class trashed. This class, however, I think we can still have. So on Thursday, if I'm late and not here at 3:15, don't give up on me. I'll get here as soon as I can, set it up, and have the class. If I'm not falling asleep with Benadryl, okay, if that happens, I'll get on and say, look, I'm too tired, we really can't have class, and we'll can it. But for right now, let's plan. We'll have class at 3:15. If I'm not here right at 3:15, don't give up. Come back and check every 5-10 minutes, something like that, just to see if I've come into class, and then you come in too. But check at 3:15 and then check periodically after that. All right, so now we're going back to the PowerPoint. Okay, chapter 2. Okay, come on and open. There we go. We'll go back, resume slideshow. If I can get the cursor to show up somewhere. I don't know why it's not showing. I can see where it's going, but I can't see it. This is such a pain in the neck. So let me go here. There. I just was on it. Okay, I'll go over here from current slide. Okay. All right, now we found it finally. Okay. Does anyone know the difference between speed and velocity, or is there a difference between speed and velocity? Anyone? Okay. It sort of has that connotation, but in reality, that may be how we use it sometime, but in reality, in everyday language, velocity and speed really mean about the same thing. But in physics, they don't. What was the difference? Okay. Okay. You're sort of saying the same thing I think he was saying, but, and that's probably how we think of it, but here's what the difference is. Velocity is a vector quantity. Speed is a scalar quantity. Speed is just how fast you're going. Velocity is how fast in what direction you're going. So that's the difference in physics. Velocity has a direction associated with it, speed does not. So let's say I was driving from here to Bessemer, okay? And let's say that my average speed was, what do we say, 40 miles per hour. Well, that's speed. How far I traveled, how long it took. Same speed coming back, then it would be 40 miles per hour coming back. But guess what? If we're talking about velocity, that would be 40 miles per hour to the southwest and coming back. Yeah, was that? I think someone's microphone is on. Okay. Coming back would be 40 miles per hour to the northeast. So you see, velocity would include a direction, whereas speed is only a scalar quantity, a number, and that's all. Velocity has a direction associated with it. Okay? Now, it describes speed, how fast it's going, but it also adds the other component to it. Where is it going? What direction is it going? Speed just says how fast is it going. Velocity says how fast in what direction. Okay? Now, the graphical representation for velocity is that of a vector. The length of it corresponds to the magnitude, which, by the way, is the speed. The arrowhead gives you the direction that it's going. So here's the representation of this. Here's a car traveling, or a vehicle traveling due east at 30 kilometers per hour. City street, not too fast, okay? 30 kilometers per hour. Here is the same vehicle, but he's now going 60 kilometers per hour. So you see the arrow is exactly twice as long as this one, okay? So that would indicate twice the speed. The velocity would be twice the velocity as well in the same direction. Now, this car over here is traveling 60 kilometers per hour to the northwest. The speeds are exactly the same, 60 kilometers per hour. The directions, though, are different. Here the directions are different. The directions are the same, but the speed is different. So either one of those would be a different velocity. Not a different speed. These two would have the same speed, but these two would have different velocities as well as these two, because the speeds are different. Here because the direction is different. Okay? So that's what we mean by velocity. Okay. So and we're going to be doing this in lab, so hang on to these concepts. All right. Now someone already mentioned the term acceleration when they were given the velocity definition. What is acceleration? Okay, let's step back for a moment. Okay. Speed is distance per time, the time rate of change of distance. Velocity is the time rate of change of displacement, because displacement is a vector quantity. It's not just how far you move, but which direction you moved. So velocity is the time rate of change of displacement. Well, acceleration is the time rate of change of velocity. Motion implies velocity. So the rate at which the motion changes over time. In other words, velocity over time is acceleration. Distance over time is speed. Displacement over time is now with acceleration, you can have several things happening, just like we saw with velocity. You can have your speed changing. You certainly are accelerating then. Sometimes we call it decelerating if you're slowing down. In physics, we call it a negative acceleration if you're slowing down. So that's the speed change. Or you could have a direction change, because velocity is changing. It changed from this direction to that direction. Like in the last thing, if this car down here went here and then made a really sharp turn and turned like this, he accelerated. Even though he didn't change his speed, he accelerated because he changed his direction. Now certainly if he went from here to here, he accelerated because he changed the speed. He also accelerated if he went from 60 kilometers per hour due east to 60 kilometers per hour northwest. That's an acceleration as well. And you know that, don't you? Because if you were to make that change at 60 kilometers per hour, a very sudden sharp turn like that, you'd hear your wheels going on the pavement, because they're forcing them to change your direction. That is an acceleration. We'll talk about that later. And you could have both the speed and direction changing. Of course, that would be an acceleration too. If you're traveling here at 30 kilometers per hour this way and then turn around and change 60 kilometers per hour that way, you're both changing speed and changing direction. That's definitely an acceleration. Now, as I said before, your acceleration could be negative. If you're going along pretty rapidly and then slow down, that's a negative acceleration. If you're going backwards and you speed up, that's a negative acceleration. Okay, so accelerations can be positive or negative. but it's created by a change of velocity, the vector quantity velocity, which direction matters. So therefore acceleration is also a vector quantity. Now quite often we'll talk about the magnitude of acceleration, which is just a scalar, but most of the time we'll deal with direction as well. Acceleration is a vector quantity. Velocity is a vector quantity. Speed is a scalar quantity. Displacement is a vector quantity. Distance is a scalar quantity. We'll talk about more later. Okay, so here's an example of this. If the car started at 30 miles per hour and then increases speed to 60 miles per hour, that's a change of speed, 30 miles per hour, that's how much it increased, and you would divide that by the time that it took him to go from 30 to 60. That would be his rate of acceleration. Now a lot of times with cars we talk about, say, 0 to 60 in 4.3 seconds, in 5.2 seconds, or something like that. People are bragging about how hot their car is, okay? Mine's usually hot if I leave the windows up in the summertime, but that's about the only heat I get out of it. So that would be a change of speed. That's a velocity. Also, if he went from 60 miles per hour to 30 miles per hour, that's also an acceleration. It's a negative acceleration because final minus initial. Remember, that's your delta. Final minus initial. That would be a positive acceleration in this case, a negative acceleration here. Okay, you asked for it. You got it. Here she is. Let me see if I can get her in the picture. Can you say hi, Colby? There she is. You see her? Who was asking for her? She is. She's a sweetheart, and she wants me to rub her. Yeah, she's a sweet dog. Okay. What's that again? Yes, it really was, wasn't it? Okay. And she thinks every moment's a golden moment, don't you? You sorry thing, you. Okay. So, increasing speed, that's an acceleration. We usually think of it that way. Decreasing speed is also an acceleration. It's just a negative acceleration. Down here, we have going from 30 miles per hour around the bend to, I don't know which way they go. I guess they started here. 30 miles per hour west, change to 30 miles per hour east, going around a sharp bend there. That's an acceleration. Same speed, change of direction. Or you could have a change of speed and a change of direction from 30 miles per hour to 60 miles per hour, but also changing direction. That would also be an acceleration. A little more complicated kind of acceleration, but it is an acceleration. You could also be slowing down going around the curve. They could have shown a 60 miles per hour here and a 30 miles per hour there, going around the curve, double change of acceleration. That one we wouldn't necessarily call negative. There's a part of it that's negative, but it's just a change of acceleration. So a lot of times we don't pay attention to the positive, negative, because we let our vectors do the talking and walking for us. Okay. And by the way, that was all on over here on page 31 now, or somewhere thereabout. We did skip over examples 2.2, 3, and 2.4. Let's hit those before we get to the next one. Okay, so let's go back here and do 2.3 and 2.4. Okay, I think I'll go back to the whiteboard. Okay, 2.3. A bicycle moves from rest. Ooh, what does that mean? A bicycle moves from rest. I'm going to write it down. What do you think that means? What would rest indicate to you? Not that you're tired. a bicycle moving from rest? Rest means it's not moving. When I rest, I like not to be moving. So that means 0 velocity. And what velocity? If it's from rest, that would be initial velocity is equal to 0, and it doesn't say what, meters per second. So I'll put that in, meters per second. So rest means 0 velocity. Okay. Now later we'll do a problem, maybe the very next one, that says comes to a stop. Well, the difference there is its final velocity is 0. Okay? So all sorts of those things. Later we'll talk about things that you drop them. If you drop them, I'm not going to drop this because that's an expensive pen. I'll drop this one, an eraser. Drop that. If I drop it, that means its initial velocity was 0 because it was sitting at 0. Now if I were to throw it down, then I would give it an initial velocity. Okay? But if it stopped when it hit the end, that would then be a final velocity of 0. So what we're dealing now is some subscripts here, initial and final, and that's what we get for a change of velocity. Okay, a bicycle moves from rest to 5 meters per second. Okay, where is my pen? Oh, there it is. To 5 meters per second. Now here they don't put significant digits in there. Okay, in 5 seconds. Okay, now what is this, you think? Rest was initial velocity. To 5 meters per second would be your final velocity. V final is 5 meters per second. In 5 seconds, that is your time interval, the delta t. Okay? Now, you know they never did write down the formula for you. They should have. They did in the book, but they didn't on the slide set. Sorry, I neglected to do that too. Let's go back. Well, I'm already on this. When remember it said the acceleration is basically the time rate of change of velocity. That means acceleration is equal to change of velocity over change of time. Now usually we think of acceleration as a vector quantity, velocity as a vector quantity. With the arrow on it, that means velocity. Vectors. Was there a question? Okay. The time is a scalar quantity. You never put a vector over that. Okay, so what does this mean? That means delta is always final minus initial. So that would be V final minus V initial over your time interval. And we know what those are. V final is 5 meters per second minus 0 meters per second over 5 seconds. And what do you have then? 5 minus 0 is 5. 5 divided by 5 is 1 meter per second per second. Okay? Another way you can write that, okay, somebody's microphone's on, I think. Maybe you, Jacob, I don't know for sure. Okay? Another way you can write this is 1 meter per second squared. Now, I don't know what a square second is. It's just a way of expressing it to keep you from having to write. Okay, Jacob, we're picking up some background noise. So maybe could you mute your microphone? Okay. So 1 meter per second squared. Okay. And let's see what they got. Yep, 1 meter per second squared. All right. Now let's see. 2.4 may take more distance. All right, for me to erase my slide. Okay, I'm going to clear the drawing. and do 2.4. An automobile uniformly accelerates. Now, have they already said that? I thought they hadn't, but it looks like maybe they have. I don't see where they, oh no, negative acceleration, deceleration. I'm trying to find where they define uniform acceleration. It looks like they've already done it now, but I sure don't see it in the book. I know it's in here somewhere. Okay, we'll talk about that in just a minute when we get back to the slide set, though even they talk about it here. An automobile uniform accelerates from rest. What does that mean? Okay, let's see, what are your units using here? They're using meters per second. Okay, but what is it? That's what it means, 0 meters per second, but what does that stand for? Perfect. It's a velocity because it's meters per second. It's initial because of that word from rest. Rest means 0. From rest means that's initial. Okay, from rest, and the acceleration now, acceleration is equal to 5 meters per second squared. Now, how did I know that was an acceleration? Units are your friends. Velocities are measured in meters per second. Accelerations are measured in meters per second squared. Change of velocity per unit time, meters per second per second. So that's meters per second squared. And they do this for 6 seconds. So that's your time interval, delta t, is equal to 6 seconds. Okay? What is the final velocity in meters per second? So we're looking for v final. Okay. Now, if you go back to your original equation, it was acceleration is equal to change of velocity over change of time. Okay? Now, we don't know the change of velocity because we got the initial, but we don't know the final. This is what we're looking for. What is the change? What is the final velocity? So let's break this down into what that stands for. This means v final minus v initial, those are supposed to be subscripts by the way, over your time interval is equal to acceleration. Well, we're looking for v final. That's what we're looking for. So let's get rid of everything else. Let's multiply both sides of the equation by delta t, and that will wipe out your denominator, which I'm all in favor of, and then let's add v initial to both sides. And now we got a new formula, because this now, these two add to 0. So now we have v final is equal to v initial plus a times your time interval, at. The book just puts an at up at the top of the page. They don't number the equation, but v final is equal to at plus v initial. I put v initial plus at. Usually they write it that way. I don't know why the book wrote it the other way. Okay, so now we got our formula. Now we plug in our numbers. This is what we're looking for. And of course your v initial was 0, so we don't even have to write that down. Plus acceleration, 5 meters per second squared, times your time interval. Your time interval here was 6 seconds. Okay, now again, units are your friends. Be careful with them. This second will cancel one of those 2 seconds out. And what are you left with? 5 times 6 is 30. And your units are meters per second. which is a great unit for a final velocity. So you see not that major of an acceleration can produce a quite big change of speed. If you remember from before, that 72 kilometers per hour that car was going when the guy dropped his map, that was only 20 meters per second. So this one's really flying, okay, if you accelerate for that long, 6 seconds, 30 meters per second. All right, that was example 2.4. All right, before we move on, there is a blurb at the top of the page, Science and Society. Usually these are pretty good to read. They give you a little bit of context and practical application of what we're talking about. And this is talking about transportation and the environment. Okay? And this is talking about some of the ways that we can cut down our carbon footprint, cut down pollution of the air, cut down global warming, greenhouse gases. We can do a lot of those things. And one, they say, use a bike, walk, or take public transportation whenever possible, or carpool, a good idea. Combine trips to the store, mall, work, that kind of stuff, leaving the car parked wherever possible. Don't leave it running. I hate going through drive-thrus just because that's wasted gas. I'd much rather go in. Of course, nowadays with COVID, you don't want to go in, so you almost have to do drive-thrus. And then it says purchase hybrid or electric or fuel cell powered cars whenever possible. Those are pretty expensive. We don't have one. And move to a planned community that makes use of the cars less necessary. In other words, to a place where you have your grocery store nearby, your entertainment nearby, everything close enough that you could either walk or ride a cheaper vehicle, like you see those seniors on golf carts sometimes. And then they have questions to discuss. If you feel like this is leading you to a paper topic, maybe that would be a pretty good one. So things like that are perfectly legitimate. Now, there is something else that we can talk about here, okay? And that's right at almost the last thing on page 31 or 2-7. And that's this formula. We already know one formula for average velocity. Remember, average speed is distance over time. Okay? Now, if we were doing the old lab 2, we would be using this next thing big time. Unfortunately, we're not, but you still need to know it. Another way you can refer to your average speed is if you know your initial speed, VI, and you know your final speed, VF, and now here's the catch, you've had uniform acceleration. In other words, constant acceleration. No jerking, nothing like that, constant acceleration. And you'll see in today's lab, we don't have uniform acceleration. But what you can do, add these two together, because this means average speed. What if you had two scores? You'd add them together and divide by 2. That would give you your average score. Well, the same thing goes here. Your average speed, if you have uniform or constant acceleration, add the initial and the final, because quite often you know those, and that's another way to get average speed. So then, if you had one way to calculate it here, another way here, that could give you your final velocity, knowing this without having to go through acceleration at all. Okay? So, with that in mind, so it had to be somewhere here, they're talking about uniform acceleration, but for my looking at it, I cannot see it here. Okay? Yeah, there it is. Okay. It looks like page 31, the right-hand column. The final velocity and the initial velocity are different variables than the average velocity. You cannot use either one of those for an average velocity. You may, however, calculate the average velocity from the other two variables as long as the acceleration taking place between the initial and final velocities is uniform. That's where they say it. Not a very good definition there, but from context you see that. Okay? That would be, say you were certainly cruise control would be uniform, but that's not accelerating at all because you're not changing speed. But if when you're accelerating, you got your foot on the pedal, you're just gently putting it there and you're picking up speed in a very gradual manner, usually that's uniform acceleration. Okay? Constant acceleration, uniform acceleration. That's what example 2.5 is going to get to. So let's see if I can clear what we've got here, and we'll do 2.5. Okay, now you folks that were in the Physical Science 111, you notice we hardly did any of the examples. In 112 we do basically all the examples, okay, because that's where you put the theory to work. Okay, an automobile moving at 25.0 meters per second. What you reckon that's going to be? 25.0 meters per second. What's that a measure of? The units help you out. Distance over time is speed. Now I'm going to put V. I don't know what to put, if it's V initial, V final, V bar. We don't know. Let's read a little bit more. Okay. Comes to a stop. So this is its initial speed, and it comes to a stop. This is what I was talking about before. Guess what its final speed is? If it comes to a stop, what's the speed? 0, exactly. 0 meters per second. And 0, you could put 0.00, you could put as many decimals as you want to. That's exact. Okay? In 10 seconds. So it took them 10 seconds to do so. So that would be your time interval, your delta t. Okay? When the driver slams on the brakes. Now, here's what we're assuming. Slamming on the brakes is going to be a constant force on the car. We haven't talked about forces yet, but a constant force would produce a constant acceleration. So we're going to assume it's uniform acceleration. So the question is, how far? Again, how far? And what's the answer to that? Your distance traveled. That's the unknown here. That's what we're looking for. How far it traveled while stopping. We knew it took them 10 seconds to stop. Okay? Now, since we're assuming uniform acceleration, then this is not as average speed, that's not his average speed, but how could we get his average speed? Last formula I gave you, initial plus final, just like average test. VI plus VF divided by 2. That only works because this is uniform acceleration. Constant acceleration happens to be a deceleration, but that's fine. So this would be 25.0 meters per second plus 0, final speed, meters per second divided by 2. Okay? Well, 25 plus 0 is 25. Half of 25 is 12.5 meters per second. Average speed meters per second. Exactly that. Oh boy, I'm really regretting that I did not bring up another can of Coke. Because, number one, my head is closing up on me, and number two, with it being harder to breathe, I need some more energy. Again, it's hard to say which part of this is anemia and which part is just tiredness. I don't know. Okay. I couldn't hear you. Say again. No, I don't need a sandwich. I probably need a Coke. Let's see. We've been at it for about an hour and a half now, a little over an hour and a half. Let's see if we can make it to 2 hours and 15 minutes. If we can do that, then let's take a quick break and I'll go get me another Coke. That will do, I think. So let's see if I can make it that long. Unless some of you need a break now. Do you? Would you like one? You're good, or you're good to take a break? Second? To continue. Okay, let's continue. Okay, I think what I will do that might help a little, now it's gotten warm again in here. I don't know what's going on. Either my thermostat's messed up or the temperature is changing outside some. That may be why the dog came up. I don't know. She may have wanted to go out, but we went out at lunch, so I think she's okay. Okay, so we've got an average speed now. Now we can use the formula we had before. V bar is equal to distance over the time interval. Now that we got a V bar from this formula, we can use that. So how do we get the D? Multiply both sides of the equation by your delta T. Okay, these will go out, and that gives you D is equal to average speed 12.5. My pen is doing strange things. Meters per second times your time interval 10 seconds. And what does that give you? Seconds go out here, and you have 125 meters. Wow. Okay. How far did it take him to stop if he was going at 25 meters per second initial velocity? Slams on brakes. He went basically from the back of one end zone to the back of the next end zone and a little bit further, because those end zones are about 10 yards, wouldn't you say? And that would be 100 yards between the goal lines. Another 10 would be 120. This is further than that. This would be way back there. Wow. He skidded, or took him 125 meters to stop. Okay. And that's what they got in the book too. I was thinking that seems awfully big. Let's see about example 2.6. Ha! I was starting to erase. I'm glad I didn't. I started reading it. What was the deceleration of the automobile in example 2.5? Okay. Well, what was acceleration? And I'm going to do acceleration, not deceleration. Acceleration is change of velocity over change of time. Okay? And what's your change of velocity? Always V final minus V initial over your time interval. Okay? And what was your final here? 0 minus your initial 25.0 meters per second divided by your time interval 10 seconds. So what do you get? Negative 25 divided by 10 would be a negative 2.50. You got 3 digits here, 3 digits there, put your third digit here. And what's your units? Meters per second, or you could write that as per second squared. Man, that's a pretty hefty acceleration, okay? Deceleration. Changing 2.5 meters a second every second. And it still took him more than a football field length, end zone to end zone, to stop. Okay? Got it. Now there's another pretty interesting little concepts applied there, acceleration patterns. It's worth a read, and I've actually seen a couple of labs before that use things like this, and people could actually get out there, say in a flat level parking lot if no one else is driving around, and you could measure some speeds, velocities, forces, all sorts of things, and get a good lab out of it. Now with COVID, not going to do that. Sorry, I got the hiccups. All right, let's go back to the slide set. Okay. All right. Chapter 2. Okay, now I've got my cursor. I don't know where it was before. Let's go back to acceleration. We finished that one. And uniform acceleration, this is the one I thought, where is it in the book? I couldn't see it, but we've hit it somewhere here. Maybe I should have shown this before. Uniform acceleration is constant acceleration, straight line acceleration, because remember, acceleration is a vector quantity, so if you're moving the acceleration, you're changing it. Even if it's the same acceleration, if you move it, you're changing acceleration. So it's constant straight line acceleration. That's uniform acceleration. The average velocity is simply related to initial and final velocities in that case, and here's that relationship. I'm sorry, this block here is in the way. I'll wait and see if it'll fade. There it goes. Average velocity is the sum of your initial and final velocities divided by 2. Just like 2 test scores, add them together, divide by 2, that gives you your average grade. Okay? Same deal, only now it's initial and final velocity. The reason you can do this is your acceleration is constant, not changing, so therefore the average velocity will be the sum of the initial and kinetic and final divided by 2. Okay. Now, let's go to forces. Now, the book goes into quite a bit of stuff here, and I think we'll hit some of it here too. Historical background. Now, I don't know if Aristotle actually used the term forces or we just imply from what he was saying. But Aristotle was an ancient Greek, what they called natural philosopher. There were many great Greek thinkers back then, way back, okay, long time back. There were 3 that showed up in a row that were sort of related to each other. The oldest, the first of these, was a good old guy named Socrates. Okay, and I'm trying to remember what the order of the next 2 were. I think Plato was Socrates' student, and then Aristotle was Plato's student. And those are 3 of the greatest of the Greek philosophers and natural philosophers. Aristotle was especially good in the natural philosophy range, meaning looking at nature, figuring out what was happening, trying to establish it. So here's Aristotle. Here's what he thought. He observed that, say, if someone dropped a cannonball from the top of a roof, he said that would fall faster if someone dropped a piece of paper or papyrus or something like that from the top of the roof. And sure, that's a pretty good observation, okay? So he concluded from his observation, heavier objects fall faster than lighter objects. Okay? Now remember what we said about the scientific method now. He didn't test, he just observed. You probably have seen this one too. Drop a hammer and a feather. The hammer hits the ground first. Every time. Okay? Almost every time. We'll get to that in a minute. Okay? Here's another of his observations. Objects moving horizontally required a continuously applied force. Think of it, you driving in your car on a nice level road, no hills, no valleys, just a nice level road. You always have to keep your foot on the accelerator or else you're going to slow down. Now, of course, Aristotle didn't have a car. He didn't have that, but he observed objects moving horizontally required a constantly applied force under certain circumstances. Of course, he didn't test. He just observed. Third one, and this is what he did, he relied on just thinking alone, observing and thinking. And he was a good thinker, quite a good thinker. Okay, but he had some problems with that. He also looked at the objects in the heavens, the stars, the planets, and those things. The moon, okay? The moon seems to go at a constant rate without having a constantly applied force. So he had to then say, whoop, 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 whoop. This goes only for terrestrial objects, not for celestial. He said there's a whole different set of rules for celestial than terrestrial. Okay? That's a little funky, okay? That would be two different sets of rules, but it's the only way he could explain it. Okay. Along came Galileo and Newton. Now, Aristotle was probably 100 or so years before Christ. Galileo and Newton about 1400 years after Christ. Okay, so been a long time, folks. Almost 1500 years. But Galileo and Newton came along, and boy, in those 1500 years, if Aristotle said it, people believed it. No one challenged Aristotle on just about anything until along came Galileo. And for some reason, he was a doubter. And he said, let me test this. Okay, everybody says it. It sort of makes sense. Let me test it. That was the difference. Okay? Here's what he and Newton found out. All objects fall at the same rate. Okay? Oh, wait a minute. That doesn't seem right. Now, way early in my teaching, back when we were at Bessemer State Technical College, and teaching physics back then, which was basically a lot like this physical science right now, we didn't have a lab, so we couldn't do those. So every now and then I would do demonstrations for the class rather than a lab. And here's the demonstration that we did. In the building on the Bessemer campus, on the part of the building where the physics lab was, there was a closet in the back that had a stairwell. No one ever used it. In fact, it stayed locked up. So I got the folks from wherever, physical plant, to come and unlock that door for me just temporarily while I did my lab. And I went up to the 3rd floor, the highest floor in that building. Okay? And there was a window up there. So I went to the window, had the class down on the ground level. Okay, 3 floors down. And I had a 1 kilogram mass, that's 1,000 grams, and a 1 gram mass. That's 1/1000th of this. Okay, according to Aristotle, the heavier object should fall faster, right? I held them out of the window. They were watching. They may have had their stopwatches on, I don't remember. And then I dropped them, and guess what? Pop. They both hit the ground at the same time. And this one was 1,000 times heavier than the other one. Okay? Yes, all objects fall at the same rate. Okay? Now, Aristotle didn't test that. Galileo, Newton, they did. Now, the second of these, objects moving horizontally require constantly applied force, or that's at least what Aristotle observed. But what Galileo and Newton found out, no force is required for uniform horizontal motion. That means same speed. There's some caveats here, and we're going to talk about those in a few minutes. But no force required for uniform horizontal motion. Could Aristotle have been wrong? Well, he just didn't have all the information. Galileo and Newton basically tried to cover all the bases. So here's the third one. They reasoned. Aristotle relied on thinking alone, observation and stuff. They also did measurements. They measured the fall of things. They measured time it took. They measured all sorts of things. Galileo was very famous for using an inclined plane. If we were in class, that would be our lab today. We're not in class, so we had to come up with something else. That's what we'll be doing, something else. So on an inclined plane, the more you incline, the faster it goes, because you have a component due to gravity. Okay? And we talked about velocities and accelerations then. What Galileo did was do it the other way. He had a plane that then inclined here. He rolled the ball up the plane, okay? And he found out the steeper it was, the more rapidly it stopped. But then the less steep it was, the longer it went. And guess what? When it got flat, there was indication no force required. It went at the same speed. Okay. Now, they took measurements. Some of their measurements included, and here's what Aristotle's problem was. If you drop a hammer and a feather, a hammer has very little surface area, a feather has a lot, and a very light weight, so it reaches what they call its terminal velocity much faster than the hammer does. And therefore it does slow down, and seems like it takes longer to fall. But, now this really did happen. On one of the moon missions, the Apollo missions, the astronauts were out on the moon, and they took with them a hammer and a feather. And the moon has no atmosphere, no air resistance at all. The astronaut dropped the hammer and the feather simultaneously. They hit the ground at the same time. What the problem was, Aristotle didn't know or understand resistance. Okay? Galileo and Newton began to understand resistance. In the absence of any unbalanced force, they'd fall at the same rate. If there's unbalanced forces, yes, that changes it. But it's not because of the heaviness of it that may be a factor of it. Okay? Same thing true here. Aristotle noted that if you slide a box across the floor, it will slow down. Unless you keep pushing on it, it's going to stop. Well, guess what? There was friction between the box and the floor. Okay? If you slid that box across a perfectly smooth ice rink, perfectly level and smooth, it will go quite a lot further than it will across the floor. Why? More friction between the floor and the box than there were between the ice and the box, because there was less resistance. Aristotle didn't know or understand resistance. Galileo and Newton began to measure it and said, without the unbalanced force of resistance, there's no force required for uniform horizontal motion. Okay, that's the historical background. Here's a more practical deal. You have a picture in your book, very similar to this one, but you actually have the ship up above, a real picture of it. Okay? Now, I've been on a ship that's not too far from what this one looks like. when I was in the Navy, I was on an ammunition ship, which, boy, all my wires are all tangled up. Basically, this looks like a cargo ship of some nature, and that's basically what we were. When you get into port, close to land, you count on a pilot doing a lot of your navigation, and you count on tugs pushing you around. So that's exactly what we've got here. If you had this ship here, and you had two tugs, each pushing with 1,000 units to the east, then the ship is going to move with a net force of 2,000 units to the east. However, if one was over here pushing with 1,000 units to the east and the other one was on the other side, not knowing this one was there, pushing with 1,000 units to the east, the ship's not going anywhere because the net force is 0. So you don't just add forces, you add the vector forces, the directions as well as the magnitudes. Here the directions are in the same direction, you do add the magnitudes. Here they are exactly opposite each other but equal amount, so they cancel to 0. Here the tug on this side pushing is 2,000 units, a real powerful tug. This one over here is pushing with 1,000. He's wondering why the ship is moving back on him. He didn't know the tug was on the other side. The more powerful tug was on the other side. So the net force would then be 1,000 units to the west. Okay? So what is a force? A force is a push or a pull, capable of changing the object's state of motion. A push or a pull capable of changing the object's state of motion. The tug pushing here, two tugs pushing here, yeah, that's going to push the ship ahead. One pushing this way, one pushing that way, you're not going to get any change of motion. So the net force is 0, okay? Vector addition. If the larger tug was pushing this way, the smaller tug this way, the net force would be 1,000 units to the west. Okay? That's what we mean by net force. The overall effect determined by the vector sum of all the forces, and that's what we call the net force. Okay? Sometimes we'll call it total force. A lot of times we'll call it net force. Okay? A push or a pull capable of changing an object's state of motion. That's a force. Now, let me give you another example. Well, we aren't quite there yet. I'll try to remember to give you that example later. Let's move on. Let's talk about 4 fundamental forces in nature. There may be some more, but these are your big 4. The most basic of all your interactions. Now, the first of these is gravitational. That's what holds us on the planet. That basically is what keeps the planet orbiting around the sun. That keeps the moon orbiting around the earth. Okay, gravitational pull. That's what, when you step on the scales, that's what pushes down on the scales that you read your weight. That's a force. Gravitational forces are mass interactions. Okay, two objects, any two objects, no matter how big or how small, but most of the time we notice it more big things like planets, stars, galaxies, even black holes. Okay, those are incredibly massive gravitational forces. Okay, now the next force is electromagnetic forces. That's a charge interaction. Okay, now because there's only one kind of mass, just mass, okay, that gravitational force is always attractive. But with charges, there's 2 types of charges. There's positive charges and there's negative charges. Well, like charges repel each other, unlike charges attract each other. So if you have a positive and a negative, they're going to be pulled together. If you have a positive and positive, they're going to be pushed apart. A negative and negative pushed apart. Okay? That's electromagnetic charge interaction. Electricity is based on that, magnetism also. Magnetism, you have a magnet with a north-seeking pole and a south-seeking pole. If you bring two north poles together, they repel. A north and a south, they attract like crazy. Okay? So magnetism follows the same pattern. They're really part and parcel of this, of the same thing. Okay? Now, also involved in electromagnetic interactions are atoms and molecules are often held together by electrostatic forces. Okay? For instance, a sodium ion loses an electron. So that makes it a positive ion. So it's positive. A chloride ion over here picks up an electron. Okay? And there's a reason for that chemically. We'll get to that in chapter 8. Okay? But anyway, now they're opposite charges, they go together. They are attracted together, and that charge interaction holds them together in a bond that makes sodium chloride or table salt. Okay? Salt. Okay? Now, guess what? When they combine chemically, like I just described, they no longer have the characteristics they did before. Thank goodness, because sodium is a very soft metal, really, believe it or not, very soft metal that is absolutely explosive when it touches water. I mean, it explodes when it touches water. Lots of heat given off anytime it gets in touch with water. So if you were ever in a chemistry lab and you had a bottle in the back that had sodium in it, I guarantee you, you got a little bit of sodium at the bottom and a lot of oil on top of it to keep any moisture from touching that sodium. If it touched it, it's going to explode. Okay? If you ever had sodium touch your skin, it's going to suck the moisture right out of your skin, burn you big time. Okay? Lots of heat given off there. So that's sodium. Chlorine is a gas, a green gas, a poisonous green gas. So here we have an explosive metal that you would not ever think of putting in your mouth because it's going to explode, burn your mouth like crazy. You wouldn't think of doing that. Chlorine, a green poisonous gas, but when they combine chemically, electrostatically, now they become a brand new material called salt. And we put that on our food and eat it all the time. That's electromagnetic forces. Now, gravitational forces, they're actually weaker than electromagnetic forces. You think, oh, no, wait. We're being held down on the earth. We're not being floated into space by electromagnetic. Well, wait a minute. Here's the deal. I don't know if you've ever seen this experiment before. Take a rubber comb, now someone who has more hair than I do, and if your hair is nice and clean and it's not too humid of a day, okay, comb your hair with the rubber comb and then have a little pile of little pieces of paper that you've torn up into tiny little things. Hold the comb over the paper, it'll pick up the paper. Why? When you combed your hair, you rubbed electrons off your hair onto the comb, making it negatively charged, and then the little pieces of paper are neutral charge, so they're attracted to the negative charge, they're picked up. Well, guess what? They overcome the gravity that was holding them on the table. Now they move up to the comb. So the electromagnetic forces are actually stronger than gravitational. The difference, however, gravitational forces can go huge distances. I mean, from where we are now, well, the edge of our Milky Way galaxy to the black hole in the center of that galaxy, that is probably 50,000 light years. And yet, that gravitational force is still pulling it inward. Now, it's a really strong gravitational force, but it goes great distances. Electromagnetic forces, usually the range is very small When you're within the range, they're more powerful than gravitational. Gravitational has huge ranges, electromagnetic really small range, but they're more powerful in that range. Now, the next two have to do with the nucleus of an atom. Okay? Now, the nucleus of an atom is made up of neutrons, which are no charge, neutral charge, and protons, which are positive charge. Okay? Now, usually you have about the same number, few cases not, or slightly more neutrons than protons in the nucleus. So there you have a whole bunch of positive charges in an incredibly small space. Why are they not blown apart? We don't know for sure. We just call it the weak and the strong forces that involved in holding nuclei together, especially that strong nuclear force. It holds it together. Now, I'm sure some quantum mechanics people have a better understanding of how that force works, what it is. But again, incredibly powerful force, much stronger than weak forces, electromagnetic force, or gravitational forces, but the range of that force is incredibly tiny. Okay, so as the strength goes up, the range goes down. Pretty bizarre. Okay, you really don't need to know that. They threw it in here, so there it is. All right, now we're going to start talking about 2.3, horizontal motion on land. Okay, now this would have been our third lab. Were we on campus to do it? Okay, we're not. Okay, so this is the one I've got to make up. I had one from last spring when we had to leave campus, but it wasn't a very well thought out or planned lab. We just had to leave so fast I couldn't make up labs on the spot. So I'm going to try to do a better job of coming up with that. Let's see, how are we doing? 5:21. We've gone for a little over 2 hours. Let me see if I can make it for another half hour. Okay, horizontal motion on land. Now, remember Aristotle said natural motion, if that ball is rolling down the floor here, he said in time, I'm sorry, I said it backward, rolling down the floor in this direction, that's where you first pushed it, that after a while it comes, so it's, once you release it, excuse me, there's no more force applied to it. So you gave it a force. Think of a bowling ball. You picked it up, you threw it down the lane, rolled it down the lane, and it rolls and doesn't seem to slow down very much. It probably does a little bit, but not very much. Okay? That's because it's a flat, level surface, very little friction. But guess what? I can guarantee you it would, if you had a long enough alley, it would slow down over time because it's meeting air resistance here. Okay? Now it also has a little bit of friction with the floor. You know it does because you can hear it rolling. If there was no friction, there'd be no noise when it rolled down the floor. So there is some force due to friction. There's also air resistance, which is also a type of friction. Those are forces opposing the motion. If you don't have any other applied force in the opposite way, it looks like Aristotle was right. It's going to come to a stop. Okay? And it says it will eventually stop, and that's because your net force acting on it, once it left your hand, there's no more force pushing it down the floor, but you got air resistance and the friction of the floor slowing it down, which is opposing the motion. Now, if you had an applied force, goodness gracious, I don't know if I'm going to make it or not. If you had an applied force, it has to at least equal the air resistance and the friction with the floor in order for the ball to keep going at a constant speed. In that case, your net force is 0. So if the net force is negative, like it showed here, the ball's going to slow down, ultimately stop. if the net force is 0, that means the ball keeps rolling. Okay? If the net force is 0, if you gave it some initial speed and it was going at an initial speed, it moves at a constant velocity. So now I'm going to give you the example I was thinking of earlier. What if you were in an airplane? Let's say it's a 2-ton airplane. It may be way bigger than that even, okay? And you're flying in the air, nice level flight, at 500 miles per hour, okay? A jet aircraft, flying along at that, okay? What's your net force? Guess what? If you're going at a nice constant velocity, your net force is 0. Does that mean there's no forces acting on the plane? Absolutely not, okay? Because you know, if you're at a constant speed, you got the jet engines running, okay? Why are they running? Because there's air resistance. At 500 miles per hour, there's a significant amount of air resistance. Even though that plane is really sleek and aerodynamically designed and everything else, there's still quite a bit of air resistance at 500 miles per hour. Now, I remember as a young kid, probably drove my dad crazy, but I loved when we were going down the road, as long as we weren't in traffic or something like that. We lived out in the country, so we could do it. Sticking my hand out the window and feeling it pull my arm back. Okay, why? Because the air resistance was pushing my arm back. Now, if I did my hand like this, it was less. But if I did my hand like this, whoa, it took off. Felt like it almost going to pop it out of joint. Okay? Now, that's if we're going at a reasonably fast rate of speed. Slow rate of speed, I could still feel it, and I'd have to push against the air resistance. That's because the net force had to be 0 to keep my hand at a constant speed. Now, so the airplane, you know at 500 miles per hour, there's a lot of air resistance. That's why it has to keep the engines running, because the engine running has to overcome the air resistance, so the net force horizontally is 0. But guess what? The airplane up in the sky, gravity's pulling down on that plane. And I said if it's a 2-ton plane or a 20-ton plane, whatever it is, that's a lot of force pulling down. But we talked about before Bernoulli's force, which shows that the speed of air decreases the pressure, which is force per unit area, up. That's providing lift for the airplane. That's why it needs to be going at 500 miles per hour to give them enough lift to overcome the gravity. But still, even though there's enormous forces acting on the plane, lots of air resistance, lots of engine thrust from the jet engines, lots of weight pulling down from the gravity, but lots of lift from going at 500 miles per hour, giving a difference in velocities of the air to give them the lift. His net force is 0. What is engine going this way exactly balances the air resistance this way. The weight pulling this way exactly balanced by the lift provided at 500 miles per hour upward. Net force is 0. He's going at 500 miles per hour. His net force is 0 because he's going at a constant velocity. If he is slowing down, there's a net force. If he's speeding up, there has to be a net force, okay? If he's at a constant speed, the net force is 0. So that's what Aristotle didn't take into account, part of what he did. Natural motion question, is a continuous force necessary to keep it moving? No, if you're in the absence of unbalanced retarding forces. If you had no air resistance, if you had no friction with the floor, yep, you're going to go just fine, okay? But there's always a little air resistance, and there just about always is a little friction between surfaces, just about always. Now, here's a new term, a pretty important term, that of inertia. Wait a minute. Okay. Inertia is the measure of an object's tendency to resist changes in its motion, including rest. If I'm sitting in my armchair, recliner, stretched out, just enjoying myself, my wife may say, boy, you got a lot of inertia to overcome, meaning it's going to be hard for me to get up out of that chair. Okay, I'm feeling so comfortable, I'm inert. Okay, I'm not moving. That includes at rest. But see, inertia in the physics sense also means moving. So let's say that bowling ball was rolling down the floor there. Do you think you're going to want to step out there in the bowling alley and move it? I think not. You are going to have to exert a lot of force to move that bowling ball, to change its motion. Okay? I wouldn't want to kick it. You're going to hurt your foot because it's got a lot of inertia moving down that. A measure of the object's tendency to resist changes in motion. Now remember that feather? Very little inertia. It's real easy to change its motion. The hammer, don't take a lot more to change its motion. Okay, so inertia is involved with a concept we're going to get to a little bit later called mass. Okay, so let's look at what we mean by balanced and unbalanced forces. And the best place to go is out there in free space, way outside the Earth's gravitational field, way outside anybody's gravitational field. Now, will you ever get there? Probably not, okay? But you can get out there far enough away. You're not. No air resistance, nothing. So the motion continues unchanged without any unbalanced forces. If this is a satellite out there in deep space moving along, there is absolutely nothing to change its speed. So it's going to travel at a constant velocity no matter what. Straight line, constant velocity. Okay? Now, if, however, there was some type of opposing force, okay? Let's say that you fired a retro rocket. That is going to slow down the satellite. And this is a type of thing they do if they send a probe out to Mars, going along, batting along at a pretty high rate of speed through the solar system, nothing in its way, no air resistance, nothing else, going along at pretty rate of speed, nothing going to really slow it down too much. Of course, you got gravitation from the sun and stuff. But when you get to Mars, you don't want to keep going. You want to slow down enough so it goes into orbit around Mars. So you fire a retarding retro rocket. Okay? Now, that will slow it down. If you fired a rocket to leave, say, the Earth's orbit or to leave Mars' orbit and come back to Earth, then you're going to need a boost to increase the speed to get you going. Otherwise, it's going to go at a constant velocity. Constant speed, constant acceleration, constant everything. Adding a force makes it change its velocity. Slow it down, speed it up. Or have the force perpendicular to it. Now that's not going to slow it down or speed it up. What will it do? It changes its direction. And remember, a change of direction is an acceleration. Velocity may be the same speed, but if it changes direction, you change the velocity. If you change the velocity, that required a net force. Perpendicular force didn't change the speed, but changed its direction. That's an unbalanced force. Made it change its direction. Okay? So a retarding force decreases its speed, a boosting force increases its speed, a sideways force changes its direction. Now if that sideways force was sort of at an angle like that, that could speed it up a little bit and also change its direction. That's what pilots worry about with wind. Okay, if there's basically very little wind out there, they can go along fairly well. But what if a wind comes from this direction? Then that's going to speed them up a little and probably move them in a different direction. If the wind's coming a headwind, that's going to slow them down and may actually change the direction as well. And you may not notice it, not up in an airplane. You probably notice a little more on ground, but if you're way up in the airplane, there's no references to let you see you are changing your speed. Okay. Now, wow. That's all they do on horizontal motion on land. Okay. There's sort of a dumb little myths, mistakes, misunderstanding at the top of page 35. How are we doing on time? We're moving along. It says, do you walk or run in the rain? Which will get you wetter? Okay. Well, that's an interesting question, and I actually know that friends of mine that were in an honors calculus class, their professor posed that to them when we were undergraduates, and boy, some of those guys went out there and just calculated their heads off. And really all that matters is if the rain's falling at a constant speed, okay, the longer you're out there, the wetter you get. So if you move slower, you're going to get wetter. Okay, now where you get wet may make a difference. If you're running through the rain, your front is going to get wetter than the back, okay, because you're going into the rain. But if you're running through the rain, overall you get less wet because you're out there longer. Okay, I mean shorter distance amount of time. So that's sort of a dumb thing, but you can read it. I'm sure they go into other issues than that. So 2.4 is talking about falling objects. 2.3 was horizontal motion, where all you had was resistance motions. Falling objects, now you have gravity increasing your speed. And that's exactly what this shows. This is not 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 balls falling from the same place. No, this is a time-delayed photograph. You had your camera there in a perfectly, totally dark room. Your aperture is totally open. You have a ball up here being held by some force up here, and then you have a strobe light. Okay? Every, I think, 1/10 of a second it's going to flash on and then go back off again. So what you're taking a picture of is the ball on the first flash, the next flash, the next flash, the next flash. All these flashes are exactly 1/10 of a second apart, but notice the ball is increasing the speed as it falls because the distance between the flashes, the time is the same, the distance is increasing. That means the speed of fall is increasing, meaning it's accelerating downward, meaning there's a net force pulling it downward. That's gravity. Now, you know there's also a little bit of air resistance resisting that. If these were ping pong balls, it would look a little bit different. But this looks like a pool ball. That's pretty massive. It's probably going to fall at very regular patterns. Okay. All right. Yeah. Okay. Here is a formula that relates to that distance. Okay. Now this formula has some very specific constraints to it. Here's one constraint. The ball was released from rest. It had to have a 0 initial velocity. Okay. You don't know that now, but that has to be. Second constraint, where it fell from, you're considering that 0 displacement. Okay. So in other words, this would have to be the 0 up here. You couldn't have the 0 down here and have this being something else, because then you would have to have an extra term here. So this distance fallen is from this position, 0 position here, 0 velocity here. And then it falls according to 1/2 AT squared. What is A? That's your acceleration. Okay? Now, think of your units. Acceleration is measured in length per time, multiply by time, that's time squared. You cancel out the per second squared, if those are seconds squared, and that leaves you just a length, and that's indeed what you got, is a length. Now, I'm going to give you a little rule of thumb here. A lot of times with formulas in physics, if your variable is raised to the second power, quite often you're going to have a 2 in the denominator in front. Now, the book will give you all sorts of explanations for that. What it gets down to in calculus, which Isaac Newton had to develop the whole method of calculus in order to explain his principles of motion. And in calculus, this is called an integration constant. And it almost always is whatever the numerator here is has to be the denominator. Whatever the exponent here is has to be the denominator there. Okay. The units work out, that's right, as long as there's 0 initial velocity, 0 initial displacement. Okay. I'll go on and write for you what it is if you don't have those. Okay. If you don't have those, this formula would be, where is my pen? I can't find my pen. Oh, there it is. Okay. D is equal to 1/2 AT squared plus V initial times T plus D initial. If you had an initial displacement, that goes here, initial velocity goes there. Velocity is meters per second times second, so that's meters, this is meters, this acceleration is meters per second, multiplied by second twice, the per second squared goes out, this is just meters. Half doesn't have any units, so you have that. So this would what it be if you had an initial velocity and you had an initial displacement. If your V sub I is 0 and D sub I is 0, then this is certainly your formula to use. Okay. All right. Now, we're moving on to page 36, I think is about where we are here. Here are a couple of terminology type things. Falling objects, when we use the term free fall, and I was trying to see where this is first introduced, and I do not see it. Oh, there it is. It's on page 36, the very first end of a paragraph at the left-hand column. Okay, free fall. That's falling under the influence of gravity without air resistance. Now, you know the only place that's going to happen is on the moon or somewhere in a vacuum, out in space. Okay, well, out in space you do have gravity. Okay, you don't have any gravity. So basically, it doesn't happen, except for this. If your speed is low enough, if your velocity is slow enough, then the air resistance is negligible. So most of what we're going to deal with will be very slow speeds, so the air resistance is negligible. Okay? Now, the other thing about free fall, the distance is proportional to time squared. Hey, that was the same back here. Distance is proportional, distance here proportional to the time squared. Your constant proportionality, 1/2 your acceleration. There is that. Going back to what we did in chapter 1. Same thing's true of free fall here. The distance is proportional to time squared. Now, what's difference here in the horizontal thing, speed increases linearly with time. Okay? Now, what does that mean? Go back here. If you had an initial velocity, it influences by a linear relationship. Acceleration by a quadratic relationship, speed by a linear relationship. So it increases linearly with time. Okay? And the trajectories exhibit up and down symmetries. Now let's go back to this one again. I made the assumption someone dropped the ball from rest, that's number 13 pool ball, from rest, and it fell. I couldn't guarantee you that happened. If someone would have been down on the ground below this, throwing it upward at just the right speed that it would stop right when it touched that, then that would look exactly the same way. Because as the ball is going up with an initial velocity that you threw it with, now gravity is slowing that down because the acceleration due to gravity is downward and you had initial velocity upward. This is decreasing it as it goes, so the distance gets shorter in between until it comes to a stop right there. Okay, so speed increases linearly with time. That's if it's in the same direction of your, it's going downward. Trajectories exhibit up and down symmetries. They would look exactly the same. The acceleration is the same for all objects. That's what Galileo and Newton came up with. Acceleration is the same on all objects. Okay, here's that formula again. Distance is proportional to time squared, and they don't say anything very much about speed here, but it does increase with time because you're accelerating here. And the up and down symmetries work the same way. Okay, so now we have reached the point where we need to stop for lab, 5:45. So let me mark, we'll pick up next time with this slide right here. And I can't believe I don't have another mark on the page, but I don't. So this is the time we'll take. Try to keep it less than 5 minutes, but let's take a short, maybe 5-minute break. I know I need to go into the restroom. Y'all get to go anytime you want to. I don't. So let me take a quick 5-minute break, and I'll come back and we'll start working through the lab. Okay? So I'm going to stop the screen sharing here, and I think I'll discard this and get rid of that. All right, and we'll come back and pick up a new screen share when we come back and do the lab. You can see part of it right back here. Okay, it's hiding from you. All right, I'm going to stop the recording for just a minute. I mean, maybe a few minutes. So go take a quick break, bladder break. I'm going to get some more soda, something to keep me going for the next 2 hours. I don't think it'll be here 2 hours, but we'll see. So hang on, we'll be right back. Okay, any questions or other things before we move on to the lab? Anything on the book, the presentation, what we've talked about so far, anything? All right, so let's go to the lab, and let me see if I can pull it up here. There's part of it. Here's the part. Here's how you get to the lab. Now, this is and now everything's moved again, so I'm going to sort of have to move some stuff out of the way again. You can't see it, but I have a taskbar that's in the page, and I think y'all are okay for now. So let me go here. Here's our class. This is us. I'm going to click on, this is Blackboard, of course. Go and click on us, and you go to course content, go down here to weekly assignments and activities, come over here to the down arrow and click on that, and you can't see it, but it opened it up. And here I am going to move you. Jacob, you're in the way, so I'm going to scoot you up here for a bit. You can't see it, but that's what was happening. Okay. Then let's go down here and see, now it's opened up. We're on week 2 now, so open up week 2, click there, and the overview and to-do list. Okay, actually no, it just talks about what we're going to do, so you don't you can read that at your heart's content. Instructional materials, lessons, PowerPoint, blah, blah, blah. Okay, I'm going to click on that. And here two things show up. Well, number one, there's the PowerPoint slides that we were looking at today. It said recorded lectures. You can go to the YouTube videos playlist that was given last week. So I'm not going to link that every time. So you can go there and get there. Instructional videos, I don't think there were any, so I left that blank. Handouts, the research paper instructions are back on week 1, and the locator card, both of those links are back in week 1, so you can go back there. Here's the lab for this time. Same place it was last time. Now last time I had it, I did something dumb this time. I forgot how I did it. I just copy and pasted the link here. It won't open if you click on it. What I should have done, I'll just let you see this. I'll try to do this in the future. When it says edit here, you can't do this, but I can. This is how I should have copied the link. I did that. So it just copied the address, but it didn't make a web link. Next time I'll make a web link. But you can still use this. It's perfectly fine. And then here is the lab, the paper copy of what we're going to answer on the lab, just like we did last time. Here is lab 2. Okay, you can print it two-sided, one-sided if you want to. I'll just print it two-sided. Okay, and then the library link, etc., is the library link from week 1. So I didn't redo that one. So what I'm going to do now is I'm in edit mode, which you can't edit, I don't think. So I'm going to cancel that. Go back to this. Now, I'm going to have to move y'all again. Brianna, scoot back down where you were before. Okay. Now, the reason I have to do that, because I didn't make it a web link, I made it just a link. I'll have to take this web address here, copy it to the line up here, and when I do that, paste, and then click on that, and we're there. If I had done the web link, I think I could have just clicked on that. Okay, now we're back where we were last time. Remember, we went to simulations, and I don't know, did y'all get your, okay, let me also, well, I'm going to have to close them. You go to simulations, and we're doing physics simulations, so click on that. And that takes you to where we were before, and I think you can see everything here. It's alphabetical, and where we're looking at now, what we're looking for is the moving man. And I thought they must have lost it because I was looking under M's. What I didn't realize, they put it under T's. So you go way down here in the thing. Okay, there's my solar system, that's only in the M's. There's quantum, that's in the Q's. Resonance, that's in the R's. States of matter, that's in the S. Here we have the moving man. That's the one you click on. Now, last spring, I had several people, they said if it's a coffee cup looking symbol here, which is a Java simulations, a lot of people couldn't do it. So I don't know if you can do it or not. If you can, run it and play with it all you want to. If you can't, oh yeah, I am recording, so you can just pay attention to the lecture that we have here on the PowerPoint. It'll be saved to a YouTube video, so you can go and do it that way. So I'm going to click on the moving man here, and then click on the start button here. That's the triangle and the arrow, so click on that. Okay, it takes a while for this one to load. It doesn't seem like it's that complicated, but maybe it's more to it than what I thought. Okay, graphic system is initializing. Now some of you may not be able to see how long it's taking for this to start up. I think this computer has everything on it it needs. So finally it loaded. The moving man, there he is. Now, this first introduction, I couldn't figure out how to get anything worthwhile out of this at all. So I go straight to the tab up here that says charts. Now, if you have the lab form, if you printed that out already, you'll see it says go to Blackboard page for this course, go to the course content, scroll down to weekly activities, go to week 2, instructional materials, lab 2, click on lab simulation. Well, that was that thing. You can't click because I didn't put it as a web link, but you can copy it like I did. Okay. When you get into that, click on simulations, then on physics, scroll down to moving man. Click on it, click on the triangle. We've done that. Now it says click on the charts tab at the top of the page. That's it right there. Okay. So I'm going to click on that. Now, we will be using predominantly this position. That's where we're going to get most of our data. We're going to compare it to what it has in velocity. But velocity is not going to be all that helpful. The acceleration is almost no good at all. Okay, I'm sorry about that. I haven't figured out how to get it to smooth out. I guess I'm not smooth enough with this. I'm too jerky. I don't know what's going on, but I can't figure it out. Now, to start with, note the time when the man starts. Okay, it says click on the start icon at the bottom of the page. That's the circle with the triangle in it again. That's going to get us started. Now, the only thing that starts then is the timer. Okay. Now, as soon as I click on that and say I have to be down here to click on it, then I have to get my cursor up here and start moving the man around. So there will be some time that elapses. So here's what I want you to focus on your lab. Does anyone have it printed off already? Anybody? I do. You do. Okay. Okay. Did you not see where I was? Okay, let me go back to okay, where was I now? I hate to yeah. I'm afraid when I do this I'm going to lose them, but that's okay. I'm going to minimize that. Let's go back to, yeah, that's where I'm trying to go. Okay, yeah. I'm going back to it now. I thought it was still open, but it's not. So I'm going to the plus up here, and I got to get back to it. It's where I was before. Back to Blackboard. So if you're in Blackboard, then go to courses, not activity stream. I've never found any use for activity stream. Maybe there is. And like Angelita was saying, you have to find the course. Now, you probably don't have nearly as many courses as I do. I have to scroll all the way down and get to this course. There it is. Click on the course. You're in content. Scroll down here like Angelita was saying. I think it was Angelita, wasn't it? To weekly assignments. Oh, who was that? Valerie. Okay, thank you, Valerie. Okay. To weekly assignments, click on that, go down to week 2, like Valerie was saying, and then scroll down, and it's in the instructions too, but if you don't have it printed, you can't read the instruction, and it says instructional materials, lesson plan, blah, blah, blah. Click on that, and under labs, there is the thing. If I had done it correctly, you could just click on that and go, if that was a web link. I didn't, so you have to copy this, paste it up here in the command line, and then it'll take you to it. Now that's for to get to the moving man. To get your lab, I didn't say this, I should have. What you have to do here, you see when I put my cursor here, it doesn't underline. So you have to come over here to the 3 dots that they call an elliptical, or I don't know why they call it that. Click on the 3 dots and it says download original file. When you click on that, you'll see it start downloading over here in the lower left corner. When it finishes its download, click on it, it comes up, and this is what it looks like. It's 2 pages. There's the first page. There's the second page. Okay, so somebody has it printed already. If you don't have it printed, I would say number, you don't have to do it all now, but you will be numbering 1 to 33, so you'll know when you do print it off, you can match them up. Okay, and I'm going to tell you what you'll be doing. Okay, so you print this off, or however you want to do it from here. I've already got it, so I'm not going to download it again. So once you have that, let's go back to the simulation. Where was it? There it is. Okay, so let me move you guys out of the way again, I think. Let me see. Yeah, y'all are out of the way there. Okay, me too, by the way. Okay, I'm going to do it, but y'all are going to have to be participating because you have to, well, just to get the data, okay? I'm going to be focusing on moving the man. You got to be focusing on the time, okay? Like I say, when I hit this start button here, the time is going to start. Then I got to scoot up here and get the man and start moving the man, okay? Once I start moving the man, then here's what you're going to do. Okay, yes, okay. When I start moving the man, right, right. However you want to get it to me, but right now we've got to get the data. That's what we're focusing on now. The first bit of data you're going to get, if you see the lab here, those who've printed it already, or if you're looking at it, it says note the time when the man starts moving. It's not going to be at 0 seconds, because when I click on this, the clock starts. I can't click up here, okay, get up here and start moving him until later. So when it first starts, you'll have to note the time. I'm going to say mark the time. So you write down the time that you see, nearest 1/10 of a second. Now I'm going to take the man, I'm going to move him to the right. And right before I get to the wall over here at 10 meters, I'm going to stop the man. And then when I turn him around, you mark the time when I stop him and turn him around. So I'll say mark it again. Okay? Then I'm going to take the man over here to the left wall. And the third question is when it reaches the left wall. I'll say mark it. You write down the time then. Then I'm going to turn him around and come back here. And when I get to +10 again, I'll say mark it. You give me the time. So you're paying attention to the time. When I say mark it, you write down what time it is. And that's going to be the first 6 questions. Okay? The first question is when I start moving the man. It'll be a little bit beyond that. And then I'll say mark 5 more times up to that, and those are your first 6 questions. At the end of that 6th question, I'll probably lose track. Say stop, that's 6. Okay? So you are marking time. Okay? Now, if we don't get it right the first time, we can redo it. Okay? So let's see if we can. Okay? I'm going to hit the play. The clock starts. Okay? Now, start moving the man. What was the time? Okay? Okay? Now, I stop him, mark it again. This is going much slower than it did in the past. I don't know what's going wrong here. Okay? Stop it and mark it again. Every time I say mark, you pay attention to the time and do that. Okay? Mark it, turn them around. Okay? Tell me when I've got 6 of them. Okay? Stop, mark it, turn it around. Stop, mark it, turn them around. That's the last one. Wow, that went much slower than last time. I don't know what the difference is. I like this a lot better than I did before. We could have done a lot more. There's something weird that has happened since the last time I did this, and I don't know what it is. Okay, so now you've got your marks. You wrote down 6 times, didn't you? Number 1, when he started moving. Number 2, when he reached the right wall the first time. Number 3, when he reached the left wall the first time. Number 4, when he reached the right wall the second time. Number 5, when he reached the left wall the second time. And number 6, when he reached the right wall the third time. Right? You got those times. Okay. I don't know what they are. You've got them. Okay? Now, number 7. What was the time difference between 1 and 2? Okay, now that would be 2 minus 1. You got your calculators, you can do the subtraction. 2 minus 1. That's not the number 1. It's whatever the time you had for number 2 minus the time you had for number 1. Everybody done the calculation? Okay. Number 8. What was the time difference between 2 and 3? So the time for 3 when he reached the left wall minus the time that he reached the right wall on number 2. Do that subtraction. When you've got it, let me know. Okay, but it's going to be in the same ballpark. So that's why it's a lab. Look, when you're doing... Does that fit your other 2? It's in between 2 and 4? Yeah. Okay. Y'all don't have to have the same answers. You just have to be consistent with your answers. If we were in the lab, you'd be in different teams. You'd be measuring a ball rolling down a ramp, and everybody would have different times. In fact, I'd have you do it 3 times and average the time each time, because you never get this, or seldom will get the same thing twice in a row, even though it's the same distance, same everything. It's just how quickly you are with your stopwatch. This was our stopwatch. Okay? So, anyone get number 8, the time difference between 2 and 3? Have you all answered that one? Yay or nay? No, okay. It's the answer you had for 3 minus the answer you had for 2. You can do it in your head or you can do it on a calculator.
Okay, I just want to confirm we are getting negatives, right?
Okay, yeah. Okay, no. I said, okay, it's always final minus initial. Later we're going to get some negatives, but not with time. Time is always positive. So it's 2 minus 1, 3 minus 2, 4 minus 3. Okay? Because the time was increasing the whole time, right? So take the bigger number minus the smaller number. Okay? You want the time elapsed from when he started at 0 meters till he reached 10 meters. Then the time elapsed when he went from plus 10 to minus 10. Then the time elapsed when he went from minus 10 to plus 10. That's what you're doing, your delta t's. That's what you're doing here. That's why it's a delta. Final minus initial. Okay, so everybody has a positive answer. So far for all your seconds should be positive. Not the same numbers, but they should all be positive. Okay, everybody got 8 done? Okay, number 9. What's the time difference between 3 and 4? 4 minus 3, final minus initial. Okay, whatever it is, I don't know. I have no idea because I was moving the man. I couldn't look at the time too. It sounds reasonable though. Okay, number 10, what was the time difference between 4 and 5? That's 5 minus 4. The answer for 5 minus the answer for 4. Everybody got it? Okay, I don't want to go too fast. We got lots of time here. Number 11, what's the time difference between 5 and 6? So it's your answer for 6 minus your answer for 5. That's your delta T that we were talking about in class today. Okay? Everybody got that one? Okay. Now starting with number 12, we're talking about displacement. The time was what you measured on the clock. Your displacement was what you measure on your meter stick here. Okay? So he was going 10 meters, which is a little over 10 yards. So he was, trying to get a first down every time. Okay? So what is the displacement between 1 and 2? Well, 1 started at 0 and 2 ended at 10. So what's the difference there? Final minus initial, that would be 10 meters. Perfect. Okay, what was the displacement between 2 and 3? Well, 2 was the right wall here. 3 was the left wall over here. This is your final. Minus 10 minus a 10. Now we get some negative numbers here. What would that be? No. Did he go 0 distance? He went from here to there. That's not 0 distance. Negative 10 minus 10. Minus 20 meters. You're absolutely right. This one does have a negative. When you said, are you getting negatives? I said, well, not yet. Okay. Time is always positive, but your displacement can be negative. If he was moving to the left, he's going negative. Okay. What's the displacement between 3 and 4? Remember, 3 is over here at the left wall, and he goes to the right wall. And what's your displacement? Final minus initial. His initial was minus 10. So it's 10 minus a minus 10. That's a... No. 10 minus a negative 10. Okay? Okay. You're doing a subtraction. I don't know if I'm going to be able to write on this screen or not because this is thing. Let's see if I can. No, I can't. Okay? No, wait. Okay. I'm going to go to a whiteboard. Okay. Let me clear what I had here. Okay. And let me move this taskbar out of the way here. I don't know why it goes back in the way. Okay. What we had, his final then was plus 10 minus his initial, the left wall was a minus 10. Okay? A minus times a minus is a minus times minus is plus 10. And what does that give you? 20. And sure enough, folks, 20 meters. Okay, let's go back to our, I think, say that again. Oh, yuck, I'm in the wrong place. Okay, here we go. Okay, now Yeah, this is answer to 14. Okay. Now let's think about this. Let's go back to 12. Okay. He started at 0 meters. He went to the right, which is in the plus direction, 10 meters. 10 minus 0 is 10. He went 10 meters in the right direction. Okay. That's the displacement. Positive displacement to the right. Then he went from plus 10 to minus 10. How far did he go? He went 10 meters to 0 and another 10 meters here, but he was going in the left direction. That's a minus 20. Isn't that what you got for 11? Somebody?
Yes, sir.
Yeah. Okay, then he left here. He turned around and went to the right 10 meters here and then the other 10 meters there. How far did he go to the right? Another 20 meters.
My screen is blank.
Oh, I'm sorry. I'm sorry.
That's why I can't relate right now.
Okay, I'm sorry. When I went to the whiteboard, it took it out. Let me get it back again. Can you see that? Okay, let's start over again. Number 12, number 12 is asking what was his displacement from the time he started, that's 1, until he got to the right wall. From 0 to 10, how far did he go? Positive 10. Then from this point to number 2, which is on the left wall, he went negative 20. He went 10 meters to the left here and another 10 meters to the left there. That's 20 meters to the left, which is negative 20 meters. Then when he turned here and went back to the right wall, how far did he go? Positive 20. So that's number 14, right? And then number 15, when he went from there back to the left wall, it was minus 20. Perfect. And then when he went from the left wall back to the right wall, it was a positive 20 meters. Exactly. Okay, and that took us to the end, right? Now, the next question says, calculate the average velocity between 1 and 2. That's when the time he started and he reached the right wall. Well, you've already, okay. I'm going back to the whiteboard again. Okay. Okay. Now, remember what average velocity is. V bar. That's change of displacement or distance traveled divided by the change of time. Now, you calculated the change of times before, right? The change of displacement we just did. They were either plus 10, minus 20, plus 20, minus 20, whatever. Okay? That was your change of D. Your change of T was the one corresponding to the same one, so this is going to be your average velocity. Sometimes these are going to be positive, sometimes it's going to be negative. The delta T is always positive, but the delta D could be positive or negative. So that's the formula we're going to use. So let's go back to our moving man. Is that him? Yeah, that's him. You can see that now, right? Okay. So on the number, which one are we on? Number 17. Calculate the average velocity between 1 and 2. Well, we know the displacement was 10 meters and the time difference was what you answered for number 7, because that was a time difference between 1 and 2. So divide 10 by whatever your answer was for number 7. Do you see that? So that'll be meters divided by second, and that will give you a unit of meters per second. That probably will take a calculator, so I hope you got a calculator or a phone or something you can use. Did you get that average velocity? It should be positive because your displacement was positive, your time is always positive.
Will you repeat how to do it again?
Okay. What you're doing, the average velocity between 1 and 2. That would be your answer for number 12, which is your displacement between 1 and 2, divided by your answer for number 7, which is your time difference, your delta t between 1 and 2. Does that make sense? I can tell you the answer for number 12, that was plus 10 meters. Divide that by your answer for number 7, which is some time. I don't know what time it was, but it's a positive number. If it's not a positive number, we got to go back and make sure you did your time differences in positive numbers.
Do you want us to do like 0.9 or just do the 9?
Okay, I don't know what your number was. Okay, if it was, okay,
10 divided by 0.9.
that's exactly, if that's what your number was, that's what it was. I'm going to pull up my calculator here. I don't know if you'll be able to see me do it. Okay, so there it is. Okay, and I would do 10, I'm doing this backwards, 1, 0, is that the division sign? Divided by 0.9, you said? If that's what you had, that's what you put down. 0.9, and that equals, that's it. Now, don't write all those ones down there. Round it to, I would say, your seconds would probably no more than 2 significant digits. So 11 would do, or 11.1 would do, something like that. Okay? All right. Number 18, the average velocity between 2 and 3. Well, that would be your displacement between 2 and 3, number 13, divided by number 8, the time difference between 2 and 3. Because that's what average velocity is. Change of displacement over change of time, divided by change of time. Now your displacement there was a negative 20 if I'm not wrong. So that your average velocity will now be negative because he's moving to the left. Okay? Does everyone have number 18 done? I'm only hearing a few people answer. I hope all of you are doing this, because it's going to be a lot easier to do it together like this than it is on your own. Because I don't know if you'll even be able to get the moving man to move on your own, but whatever. Okay? So what have we done? Through 18? Okay. Number 19, calculate the average velocity between 3 and 4. Well, that would be number 14, which I think was a positive 20, I can't remember for sure, divided by number 9, which is some time difference. Okay. I doubt if all these time differences are going to be the same, so you'll have to do the division every time. Everybody got number 19 done? Okay. Number 20, calculate the average velocity between 4 and 5. Well, 4 and 5 was the displacement between 4 and 5 was number 15, which I think was a negative 20 again, divided by the time difference between 4 and 5, which was number 10. So divide whatever answer you got for 15, divide that by the answer you got for 10. So I think that was a negative divided by a positive. The positive is going to be a decimal number. See what you get for average velocity. When you've got number 20 done, let me know. Now, does anyone need any questions here? I don't want to be rushing this. We got plenty of time. Plenty of time. How are we doing? Okay, let's move to 21. Oh, okay. Number 21, calculate the average velocity between 5 and 6. That will be your answer to number 16, the displacement between 5 and 6, which I think is a positive 20 again. I don't remember. Divided by 11, which was your time between 5 and 6. You got it? All right. That's number 21. Now, that was change of displacement per change of time. That was your velocity. Some were positive velocities, some were negative velocities. Okay? So what we have to do now is what's the velocity difference between 17 and 18? 17 was your velocity, average velocity between 1 and 2. 18 was between 2 and 3. Now I don't remember which was positive and which was negative, but remember it's 18 minus 17. Now if 18 was negative and 17 was positive, that's going to be a negative answer. If 18 was positive and 17 was negative, minus a minus makes that positive. So you have to keep up with your signs. I don't know what they were now. I wasn't keeping this. I'm not keeping the data. You have to keep them. So if you made that calculation, the answer to 18 minus the answer to 17. Everybody got it? Number 23. Yes, what's the question? Okay, if we need to go back and answer something, please. Yeah.
You said 18, number 18 minus what?
Okay, wait. The answer for 22, what's the velocity difference between 17 and 18? Go back to 17. That was your average velocity between 1 and 2. If I'm not wrong, that was a positive velocity. Number 18 was between 2 and 3. I'm pretty sure that was a negative velocity. Tell me if I'm wrong. Okay, so the difference between would be 18 minus 17. So that would be a negative number minus a positive number. That's going to be negative, right? Basic.
Since it got negative 22.22 for 18, you subtract that from 11.11 and you'll get a negative 33.30.
Yes, if that's what you got. I'm a little surprised at that, but I guess it could be true. Okay?
Okay, yeah, that's what I got.
All right. Number 23 is what's the velocity difference between 18 and 19? Well, 18, I'm pretty sure was a positive velocity minus a negative velocity for 18. That's minus a minus is a plus, so you add those two together, the value, absolute value together, and that gives you a average velocity, the change in velocity between 18 and 19. Right? A difference is always final minus initial.
Did you say 19 is supposed to be negative?
I'm going from my, no, 19 I thought was positive.
And 18 is negative.
18 was negative. So 19 minus 18 would be a positive number minus a minus number, which would be minus a minus is plus, so it would be adding the two numbers together to give you a bigger positive number. Correct? If you're doing it on your calculator, it'll work fine. Type in the first number, a positive number, then do your subtraction key, and then put the second number in, but make sure that's a negative number, hit equal, and it'll be the sum of the two without the signs on them. I'm pretty sure. Check me and see, make sure it's right.
Yes, it's right.
Okay. Okay. So that was number 23, right? 24, what's the velocity difference between 19 and 20? So find your velocity, average velocity in 20, which I think that's a negative number. Subtract from that a positive number for 19. That would be a minus and a minus. So basically you're adding those two together with a minus sign in front, right? Okay. And then number 25, what's the velocity difference between 20 and 21? I think 21 was a positive number, and I think 20 was a negative number. I may be wrong on that, but that would be a positive minus a minus, which is a plus again, your answer for 20, and that should be a bigger positive number. Correct? Okay. Now, we've got through 25 now, right? Now, this seems a little bizarre, but it's true. What was the time difference between 1 and 3? Now, why do we do that? Because you see, your acceleration measures a change of velocity. The first one, say, went from 1 to 2, and the next one went from 2 to 3, but you're doing your change of your velocity from the second minus the first. Well, that went from 3 to 1. So it's the difference between 1 and 3. So you do the time for number 3 minus the time for number 1. That's the time difference between those 2 points. Okay. The next one is the time difference between 2 and 4. So you do your time for 4 minus the time for 2. And times are always positive, so these should always be turning out positive numbers. A positive minus a positive is a smaller positive is always positive. Okay? Tell me if I'm going too fast. The time difference between 3 and 5. So the time for 5 minus the time for 3. And then 29 is the time difference between 4 and 6. So the time for 6 minus the time for 4. Okay? Now, the question next is, how do you calculate average acceleration? Now, I'm going back to the whiteboard and show you the formula. Okay, this is from what we did in class 2, so it's nothing new. It's what we did in class. Okay, let's do it. The acceleration is the change in velocity over the change in time. If that's what you said, you're absolutely right. Okay, that's your acceleration. Okay, let's go back to the moving man. I think that's him right there. Yeah, there he is. Okay, so what's your change of velocity? Number 30. Now, what did I say? Okay, what you do then is your velocity difference between 17 and 18. That was your answer to 22, right? Divided by the time difference that we had between 17 and 18, and that was 26. It says between 1 and 3, but those are the times that you are measuring those velocities. So it's 22 divided by 26. Not the number 22 by 26. The answer for 22, which could be plus or minus, I don't remember which it is, divided by your answer for 26, which I know is positive. Now notice your units. That would be meters per second, that's your answer for 22, divided by second again, that would be 26, that would be meters per second, or what I put down here, meters per second squared. That's what we measure our velocity in. Acceleration, I'm sorry, measures acceleration. Velocity is meters per second, acceleration is meters per second squared. Units are your friends, folks. Be kind to them. Okay, the answer to 31 would be the velocity difference between 18 and 19. That's your answer for 23 divided by your answer for 27. I don't know what the answer for 23 is. If it's plus or minus, I can't keep up. But I know your answer for 27 had better be positive. Okay. So your acceleration will be whatever your change of velocity is. Okay. Ready for 32? Don't let me rush you, but let me know when you're ready.
Can we go back to
30, okay. 30 is calculate the average acceleration between 17 and 18. So I'm going to go back to my whiteboard just so you can see the formula. Acceleration is, or average acceleration, you could have put a bar over if you wanted to, your change of velocity over your change of time. Okay? And what we're talking about here for this one, is that it? Yeah. Okay. Okay. Your change of velocity between 17 and 18 was your answer to 22. I don't remember if that was positive or negative, but it was one or the other. Okay? Divided by the time interval between 1 and 3. Because you're doing your velocities, took it between 2 times, then between 2 velocities you had a bigger time interval. So that's why we did between 1 and 3 there. Okay? So it's the answer for 22 divided by the answer for 26. That's your answer for 30. Okay? When you're through with that, we can go over 31 again if you want us to. Okay. So is everybody finished them all, or does anyone need any more explained?
We haven't did 32 and 33 yet.
Okay, 32, if you want to do that. Average acceleration between 19 and 20. You go back up for the velocity difference between 19 and 20. That was the answer to 24 divided by the answer for 28. Okay. Either people are coming in or leaving or sending chats or something. Something keeps popping up. Have I forgotten to bring someone back in the class? No, I guess they're all here. Okay. Only 9 people here now. Okay, you ready for 33? Okay. That's Average acceleration between 20 and 21, that's the change of velocity, the velocity difference between 20 and 21. That would be your answer to 25 divided by your answer for 29. Okay? Now, I want to point a couple of things out to you. They talk about this in the book, and we haven't really talked about it too much here. Well, I want all of you to finish what your calculations are. So when you finish your calculations, let me know. Okay. So it's okay to do some talking here. If someone's still working, I'll be glad to stop. Okay. Now, notice when the man was moving to the right, that meant his position was increasing. And that's what that measures. This is when we started. Remember, a little bit of time elapsed. The time is on the horizontal scale here. The displacement is on the vertical scale. You see it's going from plus 10 to minus 10. Okay? That was what his displacement was. So as time was increasing here, from the time he started, that was your initial time here on this scale, going to the right, he's going in a positive direction. That's his position. When he reached the wall on the right, he stopped and started going to the left. So now he was going down, back down to 0 here, and they continue going until he reached minus 10, which was the left-hand wall. Then he turned. Y'all made a mark there. The time here. You had the time here, time here, time here, and then he turned and went back to the right wall. Okay? That was the time you marked then. Then he stopped, turned around, and went back left again. Okay? Because he was going in the negative direction. Okay? Then he turned again. You made a mark here on the time and made a mark here, and that's basically where we stopped. Now, when we was going to the right, he had a positive velocity. Notice here, his velocity is positive everywhere that he was going to the right. This is going up. When he turned here, his velocity went negative, and it went negative from this point in time here to that point in time there, and that corresponds to from here, that corresponds to there and it was negative until he reached here again, and then when he turned here it went positive again. So his velocity is doing this when positive here, negative here, positive here, negative here, and you see positive here, negative here, positive here, negative here, positive here, and that's when we stopped. Okay, right there. We did something else. I went down, but we didn't take any measurements there. Now, the acceleration is positive when the time rate of change of velocity is positive. So if the slope of this velocity is positive, your acceleration is positive. When the slope of the velocity is negative, that means the acceleration was negative in here. When the slope here was positive, that means you're positive again. When the slope is negative, that means you're negative again. Now the acceleration has a lot more jerkiness to it. The main reason for that is I couldn't move the man at a uniform rate because I was having to slide my finger over the thing. I'd have to move back and forth on my pad. My pad wasn't long enough to get them back and forth. So that's why you pick all this trash up here. We calculated the acceleration. Now let me just ask you, that first velocity you had, that would be number 17. That was between 1 and 2 here. The average velocity, was that somewhere around +6 generally? Your answer to 17? Or a little bit higher than that? Say again? I couldn't hear. What was your answer to number 17? Okay, so it's on up there. I couldn't tell how far that went up because we go off scale. Okay, and then I'm guessing your average velocity for 18 would have been okay, so it was pretty negative. Okay, and you see it's way off scale here, so you can't tell. And then the next one was positive, next one negative. So you see your signs are in agreement with what we did here, hopefully. Positive here, negative there, positive there, negative here, positive there. The acceleration is going to be a lot harder to tell, but here it was positive accelerating, I'm guessing here, then a negative acceleration in here, looks like positive here. Is that what you're seeing? Did they alternate sort of? Yeah, 30, 31, 32, and 33. Oh, really? Interesting.
Did you all get that too? 30 was negative and the rest of them were positive?
Yeah. It seems like to me they should be alternating signs, but I may be wrong on that.
Okay, you said 30 was negative and the rest were positive?
Okay, I didn't say that, yeah. Is that what y'all got?
Yes. Oh,
Okay.
yeah, that's what it was. Mr. Fowler.
Okay, that's fine. Okay, let me check a few things. 17, 18, 19, 20, and 21. Weren't they alternating?
Yes.
Okay,
Yes.
so 17 was positive, 18 negative, 19 positive, 20 negative, 21 positive, right?
Yes.
Okay, so your velocity difference between 17 and 18 was negative. Velocity difference between 18 and 19 was positive. How about 20 and 24 between 19 and 20? Oh, really?
Mine was 0. Okay, mine are all from you guys because my first one was, my 22 was positive.
That's, I think, what they said too.
Because you said 18, the answer to 18 minus the answer to 17.
That was number 22, yes.
So
And
18 is negative, and you minus a negative number.
that would be a,
That's gonna
no, it would be minusing a positive number. Okay, that's what I wanted to check on to make sure you got your signs right. Okay, I think you just told me that 17 was positive, 18 negative, 19 positive, 20 negative, 21 positive, and 20, no, yeah, 21 positive. Okay, so the velocity difference between 17 and 18 should be negative, shouldn't it?
it's a negative 33.
Okay, and between 18 and 19, that seems like to me that should be positive, is it?
Positive 42. Yes, sir.
Okay, and between 20 and 21, seems like that should be negative again, shouldn't it? This is number 24.
Yeah, number 24 is negative.
Okay, and 25, it seems like that should be positive again, is it?
Yes, sir.
Okay, so you had alternating signs there between 22 and 25, right?
Yes, sir.
Okay. Well, that's what you were using for 30 through 33.
Yeah, I see where I missed it. I totally missed it. I didn't get a negative for number 24, but you're right. It was a negative.
Okay, good.
I'm so confused. I don't like physics. There's too many
Hey, hey,
numbers.
hey, hey, hey. We love physics, okay? That's why we needed to go it slow and take it easy. We shouldn't have been rushing so much. I think we were going a little too fast. That was probably my fault because I can't see what y'all are doing. All I can see is that silly little moving man in his tux or whatever. I don't know. But what I wanted you to see was the relationship in the graphs. A moving to the right is a positive speed. Moving to the left is a negative speed. Negative velocity. Moving to the right is positive velocity. Moving to the left is negative velocity. Moving to the right is positive velocity. And we stop there. Okay? Now, when the velocity is increasing, that was a positive velocity. So that was between your t0 and your t1. And that's pretty much exactly here positive velocity. Negative velocity was between this point here, no, I'm sorry, the t1 up here down to t2. And sure enough, you have a negative velocity between there and there. So you see, everything shifts a little bit one way or another. The problem with the acceleration, it's really hard to tell. But it looks like mostly positive here, mostly negative here, mostly positive there, kind of negative here, mostly positive here, blah, blah. Okay, so I wanted to make sure you had the alternating signs. And you think you got those right now? Okay. Okay.
I feel positive now since I went in and re-looked at everything.
Right. Okay. Take your time, look at them. All that really mattered was those first 6. When you got your times, then you calculate your time differences, make sure all those are positive, okay? And then your displacements, they alternated positive, negative. The first one was 10, the rest of them were 20s, and they alternated positive and negative. And then after that, you're doing your calculations, okay? So since the data were alternating, then the calculation should come out alternating too. So I think you're okay now. Feel better? No comment, huh? Okay. Now, if you still need to make calculations, take your time, do them. What I need to know if you have any questions. I want to be sure I get all your questions cleared before we depart from each other. We could have probably got one more trip back to the left wall if I see before. I don't know why things went much faster and it was much harder to keep up with things. Suddenly today it took its time. I went, all right. But when I practiced on this before, it just really rushed me. So I was in maybe too big a hurry today, but we got it done. I think it's okay. All right. So there are 33 blanks. You get 25 points in the lab. So not every blank is worth a full point. They're worth a fraction of a point, but you'll get a maximum of 25 over 25. Any questions? Okay. Do you want me to stay on board for a little bit longer to ask me questions? I hate to do this because the chewing's going to make noise, but I'm going to eat a couple goldfish. Pepper's farm goldfish. Say that again? Okay. Oh, it's good. Okay. Because the goldfish smile, don't they? Get this up so it won't crunch as badly. Okay. Are there any questions from anybody? Do you understand what the lab was doing? Did it feel like you got anything out of the lab? Reinforce anything we did in class? Okay, yeah. Okay, how you send it back to me, there is a place in week 2 that says lab 1. I couldn't put the things there because they didn't leave me a plus sign to put anything, but if you want to send them back through that, you can. Or you can, however you got it, you either, if it's in Word document, you can send it back that way. If you want to get it in PDF, you can do it that way. If you want to take a picture of it, you can do it that way. Now, somebody has been giving me, send me HEIC files. It seems like Blackboard will take those and I can print those, but if you send it to me through an email or Blackboard message, I'm not sure that I can print those. So if you are doing an HEIC file, I don't know what that stands for, I think it's some sort of picture file, then send that to me through the Lab 1 week 2, no, Lab 2 week 2 thing. That will do okay there. I don't think it does okay either in Blackboard messages or attached to an email. I know I've had trouble getting those open. I'll email you back or message you back and say, hey, I can't open this, could you send it to me another way? If you got a JPEG file or a PNG or some of those, my computer seems to open those with no problem. It's that HEIC or something like that. I don't know what those files are, and evidently my computer doesn't know. But Blackboard does seem to do okay with them within the Lab 1, Week 1 context there. So I know this probably doesn't make any sense to you because it doesn't make much sense to me either. I don't know what those letters, those suffixes stand for. JPEG is some sort of a picture file. I think PNG is a picture file. PDF is a Adobe file, you know, it's just a character file, and Word is a Word file. Doc is a Word file. So I understand most of those. My computer handles most of them, except for those HEICs. Now, some people have sent me files that just have a bunch of numbers in them. My computer doesn't know what to do with those, but I haven't gotten any of those lately. But the Word document, the PDF, the JPEGs, and I think PNG or something like that, seems like it doesn't have any problem with those. Okay, so if you send me something I can't read, I'll message you back or email you back and say, sorry, I can't open this, could you send it to me either through a different means or a different file name, okay, you know, file type. Did that answer your question? Okay, great. Okay, super. Are there any other questions? I'm recording this, so if you can't open the Moving Man on your own and play around with them, you can always go to the YouTube videos and watch them there. Now, it's already after 7 tonight, and we've got about 3 hours and 40 minutes on the video so far. It's going to probably take at least a couple of hours for that to load and go to Blackboard. That'll put it sometime after 9 o'clock. I'll be probably shutting down somewhere around 10. If it hasn't loaded by then it'll be in the morning sometime. I do have some time in the morning. It may be the morning before it loads on the playlist. So if you can't see it tonight, you should be able to see it. All those folks who weren't here, and unfortunately were quite a few who weren't here. I don't know what I did with my roll sheet. There it is. They are going to have to pick this up however they can. And we've had some people who I haven't seen yet, but they have turned in some work. 2 people turned in their acknowledgement forms, and 1 person who hasn't been to a class yet turned in both a lab and a test. I thought, wow. But he's been in one of my classes before, so I guess he was, I don't know. Don't know how he did it, but he did it. Okay, does anyone need me here for any more questions? I don't want to prolong this if y'all want to get busy doing something else, but I don't want to leave you hanging. So let me know if you got any more questions. Okay, everybody that way? We're down to only 7 people now. All right to go? Okay, well, I'm going to stop the sharing. What's that? I'm getting ready to, unless there's more questions. Okay. Okay, so I'm going to stop sharing. That's going to shut down the Moving Man. You won't be able to see them anymore. And if there's no more questions, I'll actually end the meeting for all of us. We're down to 6 people now. So take care. I hope to see you on Thursday, hopefully really close to 3:15. If I'm not here at 3:15, check every few minutes or so. Hopefully you'll get here. If I find out I'm not possibly going to be able to do it, then I'll try to send you a message on Blackboard. Okay?
Hope the procedure goes well.
Thank you so much. I appreciate it. All right. Bye-bye. You too. Thanks. Bye-bye.